In this video, I'll be walking through the answers to my Level 2 Mechanics workbook. A link to the PDF and a list of corrections is in the video description. Scalars and vectors. Explain the difference between a scalar and vector. A scalar only has magnitude, or in other words, size, whereas a vector has both magnitude and direction. So if I told you I was walking 5 kilometers, I have given you a scalar, but if I said I was walking 5 kilometers that way, because I've now given you a direction, this quantity is now a vector. Question 2. Complete the table below, providing each quantity with its symbol, its SI unit, or its International Scientific Unit, and identifying whether it's a scalar or a vector. Displacement and distance both have the symbol d and the SI unit of meters. The difference between them is that displacement is the word we use for a vector, whereas distance is the word we use for the scalar. Duration, or in other words time, is given the symbol delta t, where by delta I'm referring to this triangle here, which is used to represent the change in something. In this case, it's used to represent the change in time. The SI units for duration is seconds, and at this level of study we consider time to be a scalar. Velocity and speed both have the symbol v, and their SI units are meters per second. The difference is that velocity is the vector, and speed is the word we use for the scalar. Force has the symbol F, it's measured in newtons, and force has a direction, so it is a vector. Gravitational potential energy is given the symbol EP, or sometimes EG. The SI unit of energy is joules, and energy is a scalar. It doesn't have direction. Kinetic energy is given the symbol EK. Once again, it's an energy, so its units are joules, and once again, it's a scalar. Acceleration has the symbol lowercase a. Its SI unit are meters per second, and acceleration has a direction, so it is a vector. Unlike displacement and velocity, it doesn't have a scalar alternative. Mass has the symbol lowercase m, its SI unit is the kilogram, and it is a scalar. Power is given the symbol capital P, its SI unit is a watt, or in other words a joule per second, and power, like energy, is a scalar. Work is just a term for the energy used. It's given the symbol capital W. It has the unit of joules because it's essentially energy, and being an energy, it is a scalar. Question 3. Explain whether the following situations would require a vector or scalar quantity. A building inspector wants to measure the height of a deck. The height of the deck is a measurement of distance that does not factor in the direction of the measurement. The building inspector would therefore use a scalar quantity. And so, in other words, if you're measuring the height of something, the direction that you measure it isn't important, as long as you are, of course, measuring vertically. An air traffic controller is monitoring the flight path of an incoming plane. The direction of the incoming plane's velocities, as well as the direction of their displacement, are important for monitoring their flight paths. The air traffic controller would therefore need to use vector quantities. Speed. Question 1. Write an equation for delta d in terms of v and delta t. If we start with our velocity equation, we can solve this for delta t by multiplying both sides by delta t and swapping those sides around. Question 2. Write an equation for delta t in terms of v and delta d. Once again, starting with our velocity equation, what we can do is swap our v and our t quantities. The long version of why this works is if we start with this equation and then go to this equation here. If we then divide both sides by v, we get this equation here. But it's worth remembering that if you ever have an equation in this form here, you can always swap these two around. Question 3. Calculate the speed of an ambulance traveling at 1800 meters every 60 seconds. Our displacement is 1800 meters and our duration is 60 seconds. Using our equation v equals delta d over delta t, putting these numbers in, gives us 30 meters per second. Question 4. Calculate the distance a giant weta traveling at 0.32 meters per second moves in half an hour. And so our velocity is 0.32 meters per second. Our duration is 30 minutes, or in other words 1800 seconds, multiplying this by 60 seconds. Using the equation we solved above for delta D, putting our numbers in, gives us 576 or 580 meters to two significant figures. Question 5. Calculate the time taken for a sailfish swimming at 26 kilometers per hour to travel 150 meters. Taking our velocity of 26 kilometers per hour and converting it into meters per second by dividing it by 3.6. Our distance is 150 meters. If we use our equation from above that we solved for delta t and then put in these numbers, we get 20.77, which is 21 seconds to two significant figures. Question 6. The bacterium Thiovolum majus is among the fastest known swimming bacterium, capable of moving at speeds of up to 610 micrometers per second. If this bacterium swims at this speed for 1 hour, how far does it travel? Our velocity of 610 micrometers per second, because micro means times 10 to the minus 6, can be written as 610 times 10 to the minus 6. Our duration of 1 hour is 60 minutes, or in other words, 3,600 seconds. Using our equation for delta D and putting our numbers in, gives us 2.196, or 2.2 meters to two significant figures. Thiovolum majus has a typical body length of 10 micrometers. Calculate the time it would take for this bacterium moving at 610 micrometers per second to travel 100 of its body lengths. 100 of its body lengths is 1,000 micrometers, and its velocity is once again 610 micrometers per second. So to find our time, we can use our solved time equation, put in our numbers, where we can leave the units as micrometers, because we're dividing these numbers and the micro will cancel out. That gives us 1.639, or 1.6 seconds to two significant figures. In 2012, a cheetah named Sarah was observed running at 27 meters per second, the fastest recorded speed of any land mammal. Assuming Sarah's body length to be 1.5 meters, calculate the time it would take her to travel 100 body lengths. 100 of her body lengths is going to be 150 meters. Her speed was 27 meters per second, so if we take our duration equation, put in those numbers, that gives us 5.56 or 5.6 seconds to two significant figures. Question 7. In 1967, Burt Munro set a land speed record on his modified Indian motorcycle at the Bonneville Salt Flats. He reached a top speed of 295.44 km per hour, or 82 meters per second to two significant figures. If he maintained this speed for 10 seconds, calculate the distance he would have traveled. Knowing his velocity of 82 and duration of 10 seconds, using our distance equation, putting in our numbers, gives us 820 meters. In a qualifying run, he covered 5 kilometers at an average speed of 75 meters per second. Calculate the time taken for him to complete this run. Our distance of 5 kilometers is 5,000 meters. We have a velocity of 75 meters per second. Using our duration equation, putting our numbers in, gives us 66.67 or 67 seconds to two significant figures. If he covered a distance of 6 kilometers in 80 seconds, calculate his average speed. Our distance of 6 kilometers is 6,000 meters. Our duration is 80 seconds. Using our velocity equation, putting our numbers in, gives us 75 meters per second. Question 8. The average human reaction time is 0.25 seconds. The driver of a car traveling at 100 kilometers per hour notices a disheveled man in a shrimp hat running in the middle of the road. Calculate the distance the car travels before the driver is able to react. So we have our reaction time of 0.25, the car's velocity of 100 kilometers per hour, which dividing that by 3.6 gives us 27.78 meters per second. Using our displacement equation, putting these numbers in, gives us 6.945 or 7.0 meters to two significant figures. Calculate the distance if the car was instead traveling at 110 kilometers per hour. We have our same reaction time, our velocity of 110, which we can divide by 3.6 to find 30.56 meters per second. Using our displacement equation once again, putting in our new velocity, gives us 7.64 or 7.6 meters to two significant figures. Acceleration. Question 1. Write an equation for delta v in terms of a and delta t. Multiplying both sides by delta t and swapping the sides around gives us delta v equals a delta t. Question 2. Write an equation for delta t in terms of a and delta v. We can swap these two around, which gives me delta t is delta v over a. Question 3. Calculate the acceleration of the following. Rocket Lab's Electron rocket starts from rest and reaches a speed of 2,200 meters per second in 9 minutes. We have its change in velocity. Its duration is 9 minutes, which we can multiply by 60 to find 540 seconds. Using our acceleration equation, putting our numbers in, gives us 4.074 or 4.1 meters per second to two significant figures. A police car traveling at 90 kilometers per hour spies a stolen vehicle and accelerates to 110 kilometers per hour in 5 seconds. Our change in velocity is the difference between 110 and 90, which is 20 kilometers per hour, which we can divide by 3.6 to convert to meters per second. Our duration is 5 seconds, which we can put into our acceleration equation, which gives us 1.111 or 1.1 meters per second to two significant figures. Question 4. Calculate the final speed of the following. A drone accelerates at 2 meters per second for 10 seconds starting from rest. We have our acceleration and we have our duration. Using our equation above that we solved for velocity, putting these numbers in, gives us 20 meters per second. A train accelerates at 0.5 meters per second for 50 seconds, starting from an initial speed of 20 meters per second. We have our acceleration, we have our initial velocity, and we have our duration. We can use our equation that the change in velocity is acceleration times duration, where for the change in velocity, we're replacing delta v for the final minus initial. We can solve this for final velocity by adding vi to both sides, put our numbers in, giving us 45 meters per second. Question 5. Calculate the time it takes for the following to accelerate. A greyhound accelerates at a rate of 1.5 meters per second from a speed of 8.2 meters per second to reach a final speed of 20 meters per second. We have our acceleration and our initial and final velocities. Using our equation solved for duration, replacing our delta v with delta f minus vi, putting all the numbers in, gives us 8 seconds. A truck accelerates from 15 meters per second to 25 meters per second at a rate of 2.1 meters per second. We have our acceleration. Our change in velocity is 25 minus 15, which gives us 10 meters per second. Using our duration equation, putting in our numbers, gives me 4.762 or 4.8 seconds to two significant figures. Question 6. A bungee jumper accelerates downwards from rest at 9.8 meters per second. Calculate their velocity after 1 second. We have the acceleration, we have the duration. Using our equation for the velocity, putting in our numbers, gives us 9.8 meters per second. Calculate the time it would take for them to reach a velocity of 15 meters per second. Our velocity is 15, our acceleration is 9.8. Using our equation for duration and putting these numbers in, gives us 1.531 or 1.5 seconds to two significant figures. Question 7. A Haast eagle resting atop a high branch spots a kiwi 160 meters away and begins a dive. It accelerates to 50 meters per second in 5 seconds, then maintains this speed for the remaining 35 meters. Calculate the eagle's average acceleration during the first 5 seconds of its dive. Our change in velocity in the first 5 seconds is 60 meters per second, which it reaches in 5 seconds. Using our acceleration equation and putting these numbers in, gives us 12 meters per second. Calculate the total duration of the eagle's dive. Plotting this on a velocity time graph, we have our first 5 seconds over which the eagle is accelerating, and then we have the second unknown duration over which the velocity travels 35 meters at a velocity of 60 meters per second. We can start with our velocity equation, solve that for duration, put in our numbers, which gives us 0.5833 seconds. Now to find our total duration, we just need to add these two times together, which gives us 5.583, or 5.6 seconds to two significant figures. Calculate the eagle's average speed during the dive. We have our duration of 5.583 seconds, and a distance to our kiwi of 160 meters. Using our velocity equation, putting these numbers in, gives us 28.66, or 29 meters per second to two significant figures. If the kiwi starts running at 5.3 meters per second, when the eagle starts its dive, calculate the distance the kiwi travels before the eagle reaches the kiwi's initial position. We know that it takes this amount of time for the eagle to reach the kiwi's initial position, and we know the kiwi's velocity. The distance it travels in this time can be found with this equation here. Putting in the numbers gives us 29.59, or 30 meters to two significant figures. Distance time graphs. A tortoise and hare are competing in a 30-meter race along a straight track. A graph of their race is shown below. Calculate the top speed of the hare. To find the top speed of our hare, we first need to identify when it was traveling its fastest, which on a distance time graph is going to be the steepest section of the line, which is this one here. We see that in this section we have a change in distance of 20 meters and a change in time of 50 seconds. Using our velocity equation, putting these numbers in, gives us 0.4 meters per second. Calculate the speed of the tortoise. For the tortoise, we just have one slope over which we see a displacement of 30 meters in a time of 150 seconds. Once again, using our velocity equation and putting our numbers in, gives us 0.2 meters per second. Calculate the average speed of the hare over the entire race. We see that the hare travels a distance of 30 meters in 200 seconds. Putting these numbers into our equation gives us 0.15 meters per second. Calculate the time it would have taken the hare to finish if it had continued at its initial speed. Its initial speed was our 0.4 meters per second, and our total race distance is 30 meters. The time it takes the hare to travel this distance at that speed is given by this equation. Putting our numbers in gives us 75 seconds. And if we check our answer by continuing our line here, we indeed see that if the hare was traveling at this speed, it would cross our 30-meter line halfway between our 50 and our 100, which is 75 seconds. Speed time graphs. The National Institute of Water and Atmospheric Research, or NCEA, is tracking the movements of Bubbles, a young great white shark. A graph of her motion is shown below. Calculate Bubbles' acceleration between 3 and 4 minutes. So we're looking at this section here, which represents a duration of 1 minute or 60 seconds, and a change in velocity of 6 meters per second. Acceleration is the change in velocity over duration. Putting these numbers in gives us 0.1 meters per second. Calculate the distance Bubbles travels in the first 2 minutes. To do this, we need to find the area underneath this curve. We can do this by first finding the area of this rectangle, which is our 0 to 1 minutes. Change in distance is speed times duration. The speed is 2, the duration is 60 seconds, which gives us 120 meters. We then find the area of this triangle here, which is our 1 to 2 minutes. For this, our displacement is calculated the same, except because this is half the rectangle, we half the equation, which gives us 60 meters. Our total displacement is just 120 plus 60, which gives us 180 meters. Great white sharks have been reported to swim as fast as 50 kilometers per hour. How fast would Bubbles need to accelerate to reach this speed in 5 seconds? 50 kilometers per hour divided by 3.6 gives us 13.89 meters per second. For a duration of 5 seconds, we can calculate our acceleration. Putting our numbers in gives us 2.778 or 2.8 meters per second to two significant figures. Mixed graphs. The Mars Curiosity rover, controlled by NASA's Jet Propulsion Laboratory, is exploring the surface of Mars. The rover's movements must be planned in advance due to the time delay between the planets. A 2-minute journey planned across mostly flat terrain is described as follows. The rover accelerates uniformly for 30 seconds from rest to 0.5 meters per second. It maintains this speed for 60 seconds, then decelerates uniformly to 0.35 meters per second over 30 seconds. Plot the rover's motion on the graphs below. We have graphs for distance, speed, and acceleration. There are many ways you could go about this. Personally, I find it easier to start with the speed time graph. We know that over 30 seconds, our rover accelerates from rest to 0.5 meters per second. It then maintains the speed for 60 seconds, and then decelerates uniformly to 0.35 meters per second over 30 seconds. Next, I'm going to figure out our acceleration time graph. We know that in our first 30 seconds, we can calculate our acceleration as our change in speed, 0.5, divided by our time, 30 seconds. This gives us 0.017 meters per second, which the rover maintains for 30 seconds. Then our speed doesn't change for 60 seconds, so our acceleration is 0. We can now calculate the acceleration in our last section by once again going our change in speed, which from 0.5 to 0.35 is 0.15 divided by our duration of 30 seconds gives us 0.005 meters per second. And now to draw our displacement time graph, we need to find the area underneath these three sections. For this, you can think of it in terms of half times base times height for our triangles, and just base times height for our rectangle. So in our first section we accelerate up to 7.5 meters. Now bear in mind, because we are accelerating, our slope should be getting steeper and steeper. And now add on top of this 30 meters, where we have a constant slope because we have a constant velocity. In our last section, we travel a further 13 meters, and our slope should be getting less and less, as because we're decelerating, our speed is getting less and less. Kinematic equations. Question 1. A spacecraft accelerates from rest at 9.8 meters per second to simulate Earth's gravity. How long does it take the spacecraft to reach 3.0 times 10 to the 6 meters per second, or in other words, 1% the speed of light? Because we're accelerating from rest, our initial velocity is 0. We know our acceleration is 9.8. Our final velocity is 3 times 10 to the 6. And time is what we're trying to find. The one thing we don't care about and we don't have is our distance. So we choose the equation that doesn't have distance, which is this one here. Knowing that the initial velocity is 0, simplifies this to acceleration times time. Rearranging this for time by dividing both sides by the acceleration, putting our numbers in, gives us 3.061 times 10 to the 5, or 3.1 times 10 to the 5 seconds to two significant figures. What distance will it have travelled? For this, we can choose any of the equations above, except this one here because it doesn't have distance. I'm going to choose this one because it's pre-solved for distance, and because vi is 0, we can just simplify it down to half 80 squared. Putting our numbers in gives us 4.591 times 10 to the 11, or 4.6 times 10 to the 11 meters to two significant figures. Calculate the speed of the spacecraft after 12 hours. Our time of 12 hours, if we multiply that by 60 times 60, gives us 43,200 seconds. We can use this equation here to find our final velocity. Once again, knowing that vi is 0, putting our numbers in, gives us 4.234 times 10 to the 5, or 4.2 times 10 to the 5 meters per second to two significant figures. A drone records video for a school advertising campaign. It starts from rest and accelerates at a constant rate towards a pre-chosen location. It arrives after 6.6 seconds, moving at 5.5 meters per second. Calculate the average acceleration of the drone. Our initial velocity was 0, our time was 6.6, our final velocity was 5.5, and we want to find the acceleration. The one thing we don't have and don't care to find is our distance, so we choose the equation without distance, which, because vi is 0, simplifies to acceleration times time. Solving for acceleration by dividing both sides by t, putting in our numbers, gives us 0.8333 or 0.83 meters per second to two significant figures. Calculate the maximum displacement between the starting position and the filming location. We can use this equation to find the distance, where because vi is 0, we simplify this to half at squared, put in our numbers, gives me 18.15 or 18 meters to two significant figures. Explain why the actual displacement might differ from the maximum displacement calculated in the previous question. The drone may not have flown in a straight line. If it instead took an indirect path, then its actual displacement would be smaller. For example, if the drone traveled in a straight line of 18 meters, if it instead traveled the same distance but in an indirect path, although it's traveled the same distance, the displacement is smaller. Question 3. The greatest sprinter of all time, Usain Bolt, competes in a race against a Nissan Cube, the greatest race car of all time. Both start from rest and accelerate at a constant rate. Usain Bolt accelerates at 9.5 meters per second to a top speed of 12 meters per second. The Nissan Cube achieves a top speed of 50 meters per second in 14 seconds. Calculate the time taken for Usain Bolt to reach his top speed from rest. He accelerates at 9.5, reaches a top speed of 12, and starts with a velocity of 0. We want to find the time, so we can use this equation here. Vi is 0, so we just have at. Solving for time by dividing both sides by acceleration, putting our numbers in, gives us 1.263 or 1.3 seconds to two significant figures. Calculate the distance Usain Bolt travels in this time. To find our distance, we can use this equation here. Vi is 0, so we just need to put in our numbers, which gives me 7.577 or 7.6 meters to two significant figures. Calculate the acceleration of the Nissan Cube. The top speed of the Nissan Cube is 50 meters per second. It achieves this in 14 seconds, starting from rest, with an acceleration that we're trying to find. The quantity that we aren't given and we don't care to find is our distance, so we can choose the equation without our distance. Vi is 0, so this simplifies to at. Divide both sides by t to solve for acceleration. Put our numbers in, which gives me 3.571 or 3.6 meters per second to two significant figures. Calculate the distance the Nissan Cube travels while accelerating to its top speed. Using our equation for distance, with Vi being 0, putting our numbers in, gives me 350.0 or 350 meters to two significant figures. If the total race was 50 meters, which competitor crosses the finish line first? Assume both continue at their top speeds. For Usain Bolt, we know that for the first 7.577 meters, it took him 1.263 seconds. For the remaining distance, because we have a constant velocity, we can use our velocity equals distance over time equation, which we can solve for time. Our remaining distance is 50 minus 7.577, which he travels at his top speed of 12, which takes him 3.535 seconds. His total time is these two times added together, which gives us 4.798 or 4.8 to two significant figures. For our Nissan Cube, we know that it takes 350 meters for it to get up to its top speed, so it's not going to achieve this in our 50 meter race. We can therefore just find the time it takes for it to accelerate this distance. For this, we can use this equation once again, where to solve for time, we first multiply both sides by 2 and divide them by a. Now to get rid of our square, we square root both sides, put our numbers in, gives us 5.292 or 5.3 seconds to two significant figures. Our Nissan Cube takes longer, so Usain Bolt finishes first. Would the result change if the total race distance was instead 100 meters? For Usain Bolt, we just need to repeat this calculation here. except that instead of 50, we are now racing to 100. So for that last section, we get 7.02 seconds. For our total time, we add this to our 1.263, which gives me 8.965 or 9.0 seconds to two significant figures. For our Nissan Cube, we reuse this equation here, except now for our new distance of 100, which gives me 7.484 or 7.5 seconds to two significant figures. And so, would the result change? Yes, it would. The Nissan Cube would now finish first. Question 4. An 8 times 10 to the 2 kilogram asteroid is detected heading for Earth at a constant speed of 25 kilometers per hour. A mission is planned to install a thruster on the asteroid to redirect it away from its collision course. The thruster is designed to operate for 4 hours and change the asteroid's velocity by 2,000 kilometers per hour. Assuming the thruster applies a constant force, calculate the asteroid's acceleration. If we're applying the force for a duration of 4 hours, multiply that by 60 times 60, and we get 144,000 seconds. The asteroid's change in velocity is 2,000 kilometers per hour, which we can divide by 3.6 to find 555.6 meters per second. Acceleration is our change in velocity divided by duration. Putting these numbers in gives me 0.003858 or 0.0039 meters per second to two significant figures. The thruster applies the force at a right angle to the asteroid's initial velocity. Calculate the new speed of the asteroid. So we have our asteroid's initial velocity. We have the change in velocity we're going to cause with the thruster, which is at a right angle. The vector combination of these two is our total velocity here, v, where we know that vi is 25,000 kilometers per hour, which divided by 3.6 is 6,944 meters per second. Since v is our hypotenuse, we can use Pythagoras to find it. Putting our numbers in gives us 6,966 or 7,000 meters per second to two significant figures. If the asteroid's path must be changed by at least 3 degrees to avoid collision, determine whether the mission could successfully divert the asteroid. So given our change in velocity, we want to find the angle between our initial velocity and our final velocity v. This angle here. Knowing our initial velocity and knowing our change in velocity, we can just use the TOA relationship in SOHCAHTOA, which is that tan of the angle is equal to our opposite side, which is our delta v, divided by our adjacent, which is vi. Now, given that we've calculated our v up here, you could also use the SOH or the CA relationships. Rearranging this equation for our angle by taking the inverse sine of both sides, putting in our numbers, gives us 4.575 or 4.6 degrees to two significant figures. 4.6 is greater than 3, so the answer is yes, we will successfully divert the asteroid. Question 5. The 11,000 kilogram thrust SSC supersonic car set a land speed record in 1997. If the thrust SSC accelerated uniformly from rest to a top speed of 340 meters per second in 25 seconds, calculate its average acceleration. Our initial velocity is 0 because it's accelerating from rest. Our final velocity is 340. We know the time is 25, and we're trying to find the acceleration. So we can use this equation here. Vi is 0, so we get Vf equals At. Solving for acceleration by dividing both sides by t, putting our numbers in, gives us 13.6 or 14 meters per second to two significant figures. Calculate the distance the thrust SSC would travel while accelerating. So we're now trying to find our distance. Using our distance equation here, our initial velocity is 0. So this becomes half at squared. Putting in our numbers gives me 4,250 or 4,300 meters to two significant figures. After reaching its top speed, if the thrust SSC decelerated to a stop over a distance of 2,000 meters, calculate its average acceleration. So we have a distance of 2,000, an initial velocity of 340, we're decelerating to a stop, so our final velocity is 0, and our acceleration is what we're trying to find. The one thing we're not given, and we don't care to find, is our time, so we can pick the kinematic equation without time. Knowing that Vf is 0, we can just subtract Vi squared from both sides, and then divide both sides by 2d, put in our numbers, which gives me negative 28.9, or negative 29 meters per second to two significant figures, where our negative indicates that our acceleration is in opposition to our initial velocity, which is what we'd always expect when something is decelerating. Calculate the time it would take the thrust SSC to come to a stop. To find our time, we can use this equation here. Vf is 0, so we just subtract Vi from both sides, and then divide both sides by a to solve for our time, put in our numbers, which gives us 11.6, or 12 seconds to two significant figures. Question 6. A train is traveling at 50 km per hour when the conductor notices a box of Labrador puppies on the track, 300 meters ahead. The train can safely brake to a stop in 25 seconds. Convert 50 km per hour into meters per second. Taking our 50 km per hour, we first multiply by 1,000 because there are 1,000 meters in a kilometer, and divide by 3,600 because there are 3,600 seconds in an hour. Doing this is the same as dividing by 3.6 and is fairly easy to remember. That gives us 13.89 or 14 meters per second to two significant figures. Calculate whether the train can stop in time before reaching the puppies. We have our initial velocity, our final velocity of 0 as our train is coming to a stop. Our train can safely brake in 25 seconds, and we want to find the distance it will require. The quantity we don't have and don't care to find is our acceleration, so we use the kinematic equation without acceleration, where because Vf is 0, this simplifies to Vi over 2t. Putting our numbers in gives me 173.6 or 174 meters to two significant figures. Our train therefore brakes well short of our 300 meters, and so the train stops in time. Calculate the acceleration of the train as it brakes. To find our acceleration, we can use this equation here. Knowing that Vf is 0, we can subtract Vi from both sides and then divide both sides by t to solve for our acceleration. Put in our numbers, which gives me negative 0.5556 or negative 0.56 meters per second to two significant figures. Question 7. A firework rocket ignites and accelerates upwards from rest for 4 seconds at 9.3 meters per second. After this time, the fuel runs out and the rocket coasts upward until it reaches its maximum height. Calculate the rocket's velocity when the ignition runs out. Vi is 0 because our rocket accelerates from rest. It accelerates for 4 seconds at a rate of 9.3, and we want to find the final velocity. The quantity that we don't have and we don't care to find is distance, so we choose the equation without distance. Vi is 0, so this simplifies to at. Put in our numbers, gives me 37.2 or 37 meters per second to two significant figures. Calculate the height of the rocket when the fuel runs out. To find our distance, we can use this equation here, where because Vi is 0, we just get half at squared. Putting our numbers in gives me 74.4 or 74 meters to two significant figures. Calculate the distance the rocket rises after its fuel runs out. To help visualize this, we can use a velocity time graph, where initially our velocity is increasing, over which time we reach a height of 74.4 meters, as found in the last question. Following this, our velocity decreases to 0, over which time we're going to travel a height h2, which we need to find. During this time, we have an acceleration of negative 9.8 due to gravity. Our initial velocity was 37.2 meters per second, and at our maximum height, our Vf is 0, and we want to find our distance or our h2. The one quantity we don't have and don't care to find is our time, so we can use the kinematic equation without our time, where I'm using h2 instead of d. We know that Vf is 0, so we can just subtract Vi squared from both sides and swap the sides around, and then divide both sides by 2a, put in our numbers, which gives me 70.60 meters, which to find the total height we can add to our 74.4 to get 145 or 150 meters to two significant figures. Calculate the time it takes the rocket to fall from its maximum height. As it falls, it accelerates due to gravity at negative 9.8 meters per second. It's going to travel downwards 145 meters. And note that I'm using negatives because both of these quantities are downward. Its initial velocity is 0, and we're interested in the time. What we don't have and we don't care to find is our final velocity, so we can choose the equation that doesn't have that. Knowing that vi is 0, this simplifies to d equals half at squared. And now to solve for our time, we can multiply both sides by 2 and swap them around, divide both sides by a, and then square root both sides. Put in our numbers, gives me 5.440, or 5.4 seconds to two significant figures. Question 8. A pine cone falls from the top of a 25-meter tree. Calculate the speed of the pine cone just before it hits the ground. The pine cone falls 25 meters, it has an initial velocity of 0, its acceleration due to gravity is negative 9.8, and we're interested in its final velocity. The quantity we don't have and don't care to find is time, so we can choose the equation without that. Knowing that vi is 0, this simplifies to vf squared equals 2ad. Square rooting both sides, putting our numbers in, gives me 22.14, or 22 meters per second to two significant figures. Calculate the time it takes for the pine cone to fall to the ground. To do this, we can use this equation here, where because our vi is 0, this becomes at. We can solve for time by dividing both sides by the acceleration, put our numbers in, gives me 2.259, or 2.3 seconds to two significant figures. Another pine cone falls from the tree and hits the ground at 18 meters per second. Calculate the height it must have fallen from. Our acceleration is 9.8, our initial velocity is 0, it reaches a speed of 18 meters per second, and we're interested in finding the distance. The quantity we don't have and don't care to find is time, so we can choose the equation without it. Knowing that vi is 0, this simplifies to 2ad, solving for our distance by dividing both sides by 2a, putting our numbers in, gives me 16.53, or 17 meters to two significant figures. Vector components. Question 1. Bill and Bob are debating which side of a triangle is the opposite and which is the adjacent. What are they missing in order to settle this argument? The opposite and adjacent sides are determined by where the angle is. Because the angle is not identified, the opposite and adjacent sides cannot be identified either. And so if, for example, the angle was here, then this would be our adjacent and this would be our opposite. However, if instead the angle was here, then this would be the adjacent and this would be the opposite. Because no angle has been defined, these sides haven't been defined either. Question 2. Determine the horizontal and vertical components of the vectors below. Each box represents 1 Newton. No calculations are required. For our vector A, we have a horizontal of 3 and a vertical of 4. For our vector B, our arrow is going 4 backwards, which means this must be negative 4, and it's going 2 upwards, which gives us positive 2. Note that our general convention is that these directions are positive and the opposite directions are negative. So this way is positive, this way is positive, this way is negative, and that way is negative. For our vector C, we are going vertically downwards 4, so we have negative 4, and we're going backwards 1, so we have negative 1. Lastly, for our vector D, we are horizontally forwards by 3, so we have positive 3, and downwards by 3, so we have negative 3. Question 3. Calculate the horizontal and vertical components of the following vectors. A bottle rocket launches with a velocity of 30 meters per second and an angle of 40 degrees to the ground. If we look at our diagram here, our right angled triangle, we have an opposite side here and the adjacent side here. Where to find the horizontal? Our horizontal side is our adjacent, so we need to use the Ka relationship. That is that cosine of our 40 is going to be our adjacent over our hypotenuse, where our adjacent is VH and our hypotenuse is 30. Multiplying both sides by 30 gives us 30 cosine 40 degrees, which equals 22.98 or 23 meters per second to two significant figures. To find our V vertical, we're now trying to find the opposite. So we need to use the SOH relationship in SOHCAHTOA, that is that sine of our angle 40 is our opposite, which is our VV, divided by our hypotenuse of 30. Multiply both sides by 30, and we get VV equals 30 sine 40, which equals 19.28, or 19 meters per second to two significant figures. A volleyball is hit with a force of 400 newtons at an angle of 20 degrees to the vertical. In this case here, because of the way that the angle is marked, this is now our opposite, and this is now our adjacent. And so whereas before our opposite was our vertical, and our adjacent was our horizontal, for this question here, it's the opposite case. And so we do the same equations, but we swap the sine and cosines around. That gives me 136.8 and 375.9, or 140 and 380 newtons to two significant figures. Question 4. A jet boat points directly across a 70-meter wide river, flowing at 2.3 meters per second. It takes 45 seconds for it to cross to the other side. Calculate the distance the boat traveled downriver. So if we have our river, our boat is trying to go straight across, but because our river is flowing, it's going to go on a diagonal. Where the river is flowing at 2.3 meters per second, which represents this side here. And so if we know it traveled at this downriver velocity for 45 seconds, we can use our velocity equation, rearrange for displacement, putting in our 2.3 and our 45 seconds. That gives us a downriver distance of 103.5, or 100 meters to two significant figures. Calculate the total distance the boat traveled. And so if we imagine our river once again, our boat traveled 103.5 meters downriver, where the river is flowing this way. We know that the river is 70 meters wide, and we know that the boat was taking a path like this. The boat path, which is what we're trying to find, is the hypotenuse of this right-angled triangle. So we can just use Pythagoras, which gives me 124.9, or 120 meters to two significant figures. Calculate the speed of the boat relative to the flowing river. Or in other words, ignoring the velocity of the river, what is the speed of the boat? Using our velocity equals distance over time, the boat is traveling 70 meters relative to the flowing river in a time of 45 seconds. This gives me 1.556, or 1.6 meters per second to two significant figures. Calculate the speed of the boat relative to the riverbank. Using our velocity equation once again, the boat travels 124.9 meters relative to the riverbank in 45 seconds, which gives me 2.776, or 2.8 meters per second to two significant figures. Calculate the angle the boat would need to point to travel straight across the river. For this, we take the angle between our 70 meter wide river and our 103.5 meter downriver distance. This angle here is the angle our boat would need to point, which is the same as this angle here, except our boat is pointing this way to cancel out the flowing river. To find the angle, we can use the TOA relationship in SOHCAHTOA, that is that tan of the angle is our opposite over our adjacent. Solving this for our angle by taking the inverse tan of both sides, that gives us 55.93, or 56 degrees to two significant figures. Question 5. A fighter jet pilot flies horizontally at 800 kilometers per hour. To gain altitude, they angle the jet at 30 degrees to the horizontal. Calculate the horizontal and vertical components of the new velocity. So we know that our total velocity is 800 kilometers per hour. Dividing this by 3.6 gives us 222.2 meters per second. We need to split this vector into our horizontal and vertical components, given our angle 30. Knowing that this is our hypotenuse, this is our opposite, and this is our adjacent. For the horizontal, we need to use the CA relationship, which involves multiplying our vector v by cosine of the angle, to give us 192.4, or 190 meters per second to two significant figures. Our vertical side is the opposite side of our triangle, so we need to use the SOH relationship, which is to say we need to use the sine of the angle. This gives us 111.1, or 110 meters per second to two significant figures. Calculate the time it would take for the jet to climb 440 meters. We have our distance, and we have our vertical velocity. We can relate these with our time using our v equals d over t equation. Solving for t, putting our numbers in, gives us 3.960 or 4.0 seconds to two significant figures. Calculate the horizontal distance travelled during this time. Our time is 3.960 seconds, and our horizontal velocity is 192.4. Once again, using our velocity equation, rearranged for d this time, putting our numbers in, gives us 761.9 or 760 meters to two significant figures. Relative velocity. Question 1. A bus and car move towards the left at 12 and 14 meters per second relative to the road. A passenger on the bus walks towards the right at 1 meter per second relative to the bus. And a stationary pedestrian watches from the roadside. Calculate the velocity of the bus relative to the car. The bus and the car have velocities in the same direction, so we find the difference in these velocities, where these two symbols here are what we call the absolute magnitude. All they do is turn negatives into positive. So for example, 12 minus 14 is negative 2. However, the absolute magnitude of negative 2 is just 2. And so the velocity of the bus relative to the car is 2 meters per second towards the right. Since from the perspective of the car, the bus would be getting closer. Calculate the velocity of the passenger relative to the pedestrian. If the passenger was standing still, a pedestrian would see them moving at the same 12 meters per second as the bus. However, because the passenger is walking at 1 meters per second in the opposite direction, we subtract this from our 12. That gives us 11 meters per second, and the pedestrian still sees the passenger moving towards the left. Calculate the velocity of the car relative to the passenger. The velocity of the passenger relative to the road is, as we found in the last question, 11 meters per second. Because these two velocities are in the same direction, we find the difference between them, just as we did in part A. That gives us 11 minus 14, which is 3 meters per second. And from the perspective of the car, the passenger will, as in part A, be approaching. Question 2. A sheep is moving at 2.2 meters per second, following a farmer walking at 1.4 meters per second. Calculate the velocity of the farmer relative to the sheep. Their velocities are in the same direction, and so we find the difference between them, which gives me 0.8 meters per second. The sheep and farmer are initially 10 meters apart. How long will it take for the sheep to catch up? If the sheep is closing its 10 meter gap at a rate of 0.8 meters per second, we just need to use our velocity equation, solve for time, putting in our numbers, gives us 13 seconds. A sheepdog is running towards the farmer in the opposite direction at 12 meters per second. Calculate the velocity of the sheepdog relative to the farmer. Because their velocities are in opposite directions, this time we add them together, which gives me 13.4 meters per second, or 13 meters per second to two significant figures. Question 3. A bus travels along a straight section of road at 11 meters per second. An unruly passenger throws a paper plane towards the back of the bus at a constant velocity of 2 meters per second. Calculate the velocity of the paper plane relative to the road. So if we have our bus and our paper plane moving towards the back, the velocity of the paper plane due to the bus moving is our 11 meters per second, but then we need to subtract 2 meters per second as the plane is moving relative to the bus. 11 minus 2 gives us 9 meters per second. Calculate the velocity of the paper plane relative to a car overtaking the bus at 15 meters per second. The paper plane's velocity relative to the road is what we just found, our 9 meters per second. That velocity and the velocity of the overtaking car are in the same direction, and so we find the difference between them, which gives me 6 meters per second. What velocity would the car need to travel at for the paper plane to appear stationary? Since the paper plane is moving at this velocity relative to the road, for the paper plane to appear stationary, there would need to be no relative velocity between them, and so the car would need to have the same velocity, 9 meters per second. Question 4. An ill-natured kaka chases a Department of Conservation worker across a car park. The worker runs at a constant speed of 4 meters per second, while the car flies at 9 meters per second. Initially, they are 60 meters apart. Calculate the velocity of the car relative to the worker. Their velocities of 4 and 9 are in the same direction, so we find the difference between them, which gives me 5 meters per second. How long will it take the car to catch up to the worker? Given that the car is closing the gap at 5 meters per second, and that the distance is 60 meters between them, we can use our velocity equation, rearranged for time, putting our numbers in, gives us 12 seconds. The worker commandeers an e-scooter to aid their escape. The nearest shelter is 30 meters away. If the car is now 20 meters behind the worker, calculate the minimum speed the worker requires to outrun the menacing parrot. To find the worker's minimum speed, we're going to use our velocity equation here, where we know the distance the worker needs to travel is 30 meters, but we don't know how much time he has. To find that, we need to find the time for the car to reach the shelter. The car's distance is 20 meters, the distance that it is behind the worker, plus the distance from the worker to the shelter, which is 50 meters. We know that the car moves at 9 meters per second, and so we can use our rearranged time equation. Putting in these numbers gives us 5.556 seconds. And now we know the amount of time that the worker has. We can put this into our equation, which gives us 5.400 or 5.4 meters per second to two significant figures. Gravity. Question 1. At NASA's Zero Gravity Research Facility, objects fall 130 meters through a vacuum chamber. Calculate the duration that objects are in free fall. Objects that are dropped have an initial velocity of 0, will have an acceleration due to gravity of negative 9.8 meters per second. Our distance is 130 meters downwards, so negative 130, and we're trying to find the time. The one thing we don't have and don't care to find is the final velocity, so we choose the one equation without it. Because vi is 0, this just equals half at squared. We can then start to solve for time by first doubling both sides, and then square rooting and swapping them around and putting in our numbers. That gives me 5.151 or 5.2 seconds to two significant figures. Calculate the velocity of an object just before it hits the bottom. For this, the easiest equation to use is this one here, where once again, because vi is 0, this just becomes at. Putting in these numbers gives us 50.48 or 50 meters per second to two significant figures. Question 2. A 75 kilogram abseiler wishes to determine the amount of rope she will need to descend a cliff. She drops a rock and observes it takes 6.0 seconds to hit the bottom. Calculate the height of the cliff. Because the rock is dropped, we have an initial velocity of 0. We know it takes 6 seconds. We know the acceleration due to gravity, and we're trying to find the distance. The one thing we don't have and don't care to find is our final velocity, so we choose the equation without that. Vi is 0, so this simplifies to half at squared. Put in our numbers, which gives us negative 176.4 or negative 180 meters to two significant figures. Halfway down the cliff, her phone slips from her pocket. Calculate the velocity it would have just before hitting the ground. If she is halfway down, then her distance is going to be half of the value we just calculated, which is negative 88.2. Our acceleration due to gravity is negative 9.8. The object is being dropped, so our initial velocity is 0, and we're trying to find our final velocity. The thing we don't have and don't care to find is our time, so we choose the equation without time. Vi is 0, so this becomes 2ad. Square rooting both sides to solve it for our final velocity, and putting our numbers in gives us 41.57 or 42 meters per second to two significant figures. Question 3. A meteor is detected traveling at 300 meters per second towards the surface of the moon at a distance of 400 kilometers. The moon's gravitational acceleration is 1.6 meters per second. Calculate the velocity of the meteor just before it hits the lunar surface. Our initial velocity is 300. Our distance of 400 kilometers is 400,000 meters. We're trying to find our final velocity, and we know that the acceleration is 1.6. The acceleration would in reality depend on how close the asteroid is. However, for this question, we're ignoring that difference. The one thing we don't have and don't care to find is our time, so we choose the equation without it, square root both sides to solve for our final velocity, put our numbers in, which gives us 1170 or 1200 meters per second to two significant figures. Calculate the time it takes for the meteor to reach the moon's surface. For this, I'm going to choose this equation here because it's nice and simple. Rearranging it for time by subtracting VI from both sides and swapping them around, and then dividing both sides by the acceleration. Putting in our numbers gives us 543.8 or 540 seconds to two significant figures. Question 4. A mischievous cat knocks a pot plant off a bedside table. The pot takes 0.4 seconds to hit the ground below. Calculate the height of the table. We know it takes 0.4 seconds, our initial velocity is 0, our acceleration due to gravity is negative 9.8, and we want to find the distance. We therefore choose the equation without the final velocity, which is this one here. Vi is 0, so this becomes half at squared, putting our numbers in, gives us negative 0.784, or negative 0.78 meters to two significant figures. Calculate the velocity of the pot plant just before it hits the ground. To find the final velocity, we can use this equation here. Vi is 0, so this becomes at. Putting in our numbers gives us negative 3.92 or negative 3.9 meters per second to two significant figures. If the pot were caught halfway down, what would the pot plant's velocity be at that point? Halfway down is half of our distance, which is negative 0.392 meters. We can use this equation here to find our final velocity. Vi is 0, so this becomes 2ad. Square rooting both sides to solve it, putting in our numbers, gives me 2.772 or 2.8 meters per second to two significant figures. Question 5. An asteroid miner loses grip on her pickaxe. The pickaxe is released from a height of 1.5 meters and moves upwards with an initial velocity of 4 meters per second. The gravitational acceleration is 0.8 meters per second. Calculate the time it takes for the pickaxe to reach its maximum height. And just to be clear for this question, as per usual, things that are going up are positive and things that are going down are negative. And so our initial velocity is positive 4, our acceleration is negative 8. At its maximum height, the final velocity of the pickaxe is going to be 0, and we want to find the time. And so we're interested in the equation that doesn't have d, which is this one here. Rearranging this for time, knowing that Vf is 0, we just subtract Vi from both sides, and then divide both sides by the acceleration. Putting our numbers in gives us 5 seconds. Calculate the time taken for the pickaxe to fall to the surface from its maximum height. To find the fall time, we first need to find our total fall distance. For this, we're going to use this equation that we used here, where our Vi is 0, but because our pickaxe is released from a height of 1.5 meters above this, we need to add on a negative 1.5, because our pickaxe is going to fall downwards a further distance of 1.5, and downwards is, as mentioned, negative. Putting our numbers in gives me 11.5 meters. And now we can use the same equation that we just used, except now we want to solve it for time. Once again, Vi is 0, so this becomes half at squared. We can then double both sides, and then divide them by a and square root them. Put in our numbers, which gives me 5.362, or 5.4 seconds to two significant figures. If the miner drops a second pickaxe of the same size but half the mass, how would the time to fall compare with the first pickaxe? Ignore air resistance. Ignoring air resistance, all objects accelerate due to gravity at the same rate, regardless of mass. Because halving the mass does not affect the pickaxe's acceleration, it does not affect the time for it to fall. The first and second pickaxe will take the same amount of time to fall. Projectile motion. Question 1. A water balloon is thrown towards the right and follows the path shown in the diagram below. Add labelled arrows to show the forces acting on the balloon at point A, B, and C. For projectile motion, we assume that the only force acting is gravity, and we furthermore assume it's a constant size and always pointing downwards. Describe how each of the following quantities change throughout the flight. Horizontal force. There is no horizontal force at any time. This is because, as mentioned before, for projectile motion, we assume the only force acting is gravity, and gravity does not act horizontally. Vertical force. The only vertical force acting is the gravitational force, because it's the only force acting. It is always downwards, and its size does not change. Horizontal acceleration. Because there is no horizontal force at any time, there is no horizontal acceleration at any time. Vertical acceleration. Due to the constant downwards gravitational force, there is a constant downwards gravitational acceleration. Horizontal velocity. The horizontal velocity does not change because there is no horizontal acceleration. Vertical velocity. The initial upwards vertical velocity decreases to 0 as the balloon reaches its maximum height, then increases downward. And so if we were to draw this velocity, it would start off at a maximum, reduce in size as the balloon neared the top. At the top it would become 0, and then it would increase in the downwards direction. Question 2. David the Bullet Smith Jr. set the world record for the longest human cannonball flight in 2011, travelling a horizontal distance of 59 meters. He was launched from a 8-meter long cannon and reached a height of 23 meters. Calculate his initial vertical velocity. This journey was 23 meters, and his final vertical velocity at the maximum height was 0. He accelerated downwards due to gravity by 9.8, and we're trying to find the initial velocity. The one thing we don't have and don't care to find is the time, so we choose the kinematic equation without it, which is this one here. And since we know that final velocity is 0, we can make Vf squared 0. Now if we subtract 2AD from both sides and swap them around, we can then solve by square rooting both sides, put our numbers in, which gives me 21.23 or 21 meters per second to two significant figures. Assuming he returned to the same height, calculate his travel time. For this, we need to find the time it takes for him to go to his maximum height, and then we're going to double it to find our total time. To do so, I'm going to use this equation here, and once again consider only the vertical motion. We know that the final vertical velocity is 0, so our equation simplifies to VIT over 2, solving for time by multiplying both sides by 2 and dividing by VI. Putting in our numbers gives me 2.167. Doubling this gives us 4.334 or 4.3 seconds to two significant figures. Calculate his horizontal velocity. We know that he travels a horizontal distance of 59 in a time of 4.334 seconds. Because he's not accelerating horizontally, we can just use the simple velocity equation here. Putting our numbers in gives me 13.61 or 14 meters per second to two significant figures. Calculate the angle of the cannon. The angle of the cannon is going to be the angle between the initial vertical and horizontal velocities. We found the vertical in part A, and we know the horizontal doesn't change, so that's what we found in part C. And now since this is the opposite side and this is the adjacent, we can use the TOA relationship in SOHCAHTOA, which is that tan of the angle is our opposite over our adjacent. Solving for the angle by taking the inverse sine of both sides gives me 57.34 or 57 degrees to two significant figures. Question 3. A mountaineer throws a snowball horizontally at 14 meters per second from the summit of Mount Everest. If the snowball fell 8,800 meters to sea level, calculate the time it would take to fall. To do so, we can consider the vertical motion. It falls a vertical distance of 8,800, has an initial vertical velocity of 0 because it's thrown horizontally, accelerates downwards at 9.8 meters per second, and we're interested in the time. What we don't have and don't care to find is our VF, so we choose the equation without it. VI is 0, so this becomes half AT squared. To solve for time, we can first double both sides, and then divide by acceleration and square root both sides. Putting our numbers in gives me 42.38 or 42 seconds to two significant figures. Calculate the velocity the snowball would achieve as it hits the ground. We can use this equation here, where Vi is 0, putting our numbers in, gives me 415.3 or 420 meters per second to two significant figures. Calculate the horizontal distance the snowball would have traveled. There's no horizontal acceleration, so we can just use V equals d over t. Solving that for distance and putting our numbers in gives me 593.3 or 590 meters to two significant figures. Question 4. Stefan the seagull drops a seashell from a height of 8 meters while flying horizontally at a constant speed. The seashell travels a horizontal distance of 15 meters before hitting the ground. Calculate the time taken for the seashell to hit the ground. Considering the vertical motion of the seashell, it falls 8 meters. Because it's dropped, it has an initial velocity of 0. Its acceleration due to gravity is 9.8, and we're trying to find the time. We don't have and we don't care to find Vf, so we choose the equation without it. Vi is 0, so we get half at squared, solving for our time by doubling both sides and dividing by a, and finally square rooting. Putting our numbers in gives me 1.278 or 1.3 seconds to two significant figures. Calculate the horizontal speed of the seashell. Because we know the horizontal distance and we also know the time, we can just use our V equals d over t because there's no horizontal acceleration. Putting these numbers in gives me 11.74 or 12 meters per second to two significant figures. Calculate the speed of the seashell as it hits the ground. To find the total speed, we need both the horizontal speed, which we've already found, and also the vertical speed, which we haven't yet. The vertical speed can be found with this equation here. Vi is 0, so that gives us at. Putting in our numbers gives me 12.52 meters per second. The total speed is the hypotenuse of our vertical and horizontal speeds, which gives me 17.16 or 17 meters per second to two significant figures. Question 5. Dave the Olympic diver jumps from a high diving board 4.5 meters above the water with an initial upwards vertical velocity of 6.2. Calculate the maximum height that Dave reaches above the diving board. To find the height, we're considering the vertical motion. He has an initial vertical velocity of 6.2, and at his maximum height this will be 0. His acceleration is 9.8 downwards, and we're trying to find the distance. We don't have and we don't care to find the time, so we choose the equation without that. Because Vf is 0, we can just subtract Vi squared from both sides, and then solve by dividing both sides by 2a. Putting in our numbers gives me 1.961 or 2.0 meters to two significant figures. Calculate the time it takes Dave to reach this height. Using this equation here, where Vf is 0, so we just subtract Vi from both sides, dividing both sides by the acceleration, and then putting in our numbers gives me 0.6327 or 0.63 seconds to two significant figures. Calculate the total time that Dave is in the air. As we found in part A, Dave jumps up a vertical distance of 1.961 and then falls an additional 4.5 meters to the water. The total time is going to be the time for Dave to reach the maximum height, so the time for him to travel up to here, and then the time for him to fall. To find the time to fall, we can just use this equation here, where his initial vertical velocity at the top is going to be 0, and so to solve for time, we just double both sides, and then divide by a and square root both sides. Putting in our numbers gives me 1.148 seconds, which added on to our initial time gives me 1.781 or 1.8 seconds to two significant figures. If Dave hits the water 1.4 meters ahead, calculate his horizontal velocity. Because there's no horizontal acceleration, we can just use our simple V equals d over t. We know his horizontal distance, and we know his total time, which gives me 0.7861 or 0.79 meters per second to two significant figures. Question 6. A pirate ship fires cannonballs at 150 meters per second. The cannon is 5 meters above the waterline and is angled at 20 degrees. The captain orders the crew to target a navy fortification. calculate the maximum height the cannonball reaches. First of all, we need to find the vertical initial velocity, which if we imagine the cannon angled above the waterline at an angle of 20 degrees, this will also be the angle of our 150 velocity, and so the vertical component is this one here, which is the opposite side of our triangle. So we need to use sine 20 to find that, which gives me 51.30 meters per second. Our acceleration is 9.8. We know that at the top of our motion, our final vertical velocity is 0, and the distance is what we're trying to find. So we need to choose the kinematic equation without time, rearrange for our distance, knowing that Vf is 0, we subtract Vi squared from both sides, and then divide both sides by 2a, put our numbers in, which gives me 134.3 meters. And now to find our total height, we just need to add on our 5 meters that our cannon is above the waterline, which gives me 139.3, or 140 to 2 significant figures. Calculate the time taken to reach this height. To do that, we can use this equation here. Once again, knowing that Vf is 0, we subtract Vi from both sides, divide by the acceleration to solve for our time, put our numbers in, which gives me 5.235, or 5.2 seconds to 2 significant figures. Calculate the total time the cannonball is in the air. And so we've already found the time for it to reach its maximum height, but we now need to find the time for it to fall. As we found in part A, the distance it's going to fall is 139.3 meters. To find the time to fall this distance, we can use the equation d equals VIT plus half AT squared, where Vi would be 0, so we get just d equals half AT squared. We can solve this for time by multiplying both sides by 2, dividing by a and square rooting, and then putting our numbers in, which gives me 5.332 seconds. And now to find our total time, we just need to add on our time from part B, which gives me 10.57, or 11 seconds to 2 significant figures. Calculate the distance the pirate ship must be from the Navy fortification when it fires. The distance we're considering is horizontal, so we need to find our horizontal velocity. To do this, we just need to use the opposite to what we used in part A, which is the cosine relationship, which gives us 141.0. And now to relate this to our horizontal distance, we can use our V equals D over T, rearranged for distance by multiplying both sides by time, putting in our horizontal velocity and our total time, which gives me 1,490, or 1,500 meters to 2 significant figures. Question 7. A hidden bandit aims his bow at the knee of an unwary adventurer. He angles his bow 30 degrees upward and shoots an arrow with an initial speed of 50 meters per second. The arrow leaves the bow at a height of 5.5 meters above the adventurer's knee. Calculate the horizontal and vertical components of the arrow's initial velocity. Our arrow has a velocity of 50 meters per second at an angle of 30 degrees. To find our horizontal velocity, this is the adjacent side of the triangle, so we're using the ka relationship in SOHCAHTOA, which means we use the cosine. That gives me 43.30 meters per second, or 43 meters per second to 2 significant figures. Our vertical side is the opposite side, so we're using the SOH relationship in SOHCAHTOA, and so we now use sine of the angle, which gives me 25 meters per second. Calculate the time taken for the arrow to reach its maximum height. For this, we need to consider the vertical motion. Our initial vertical velocity is 25. At our maximum height, the velocity will be 0. Our acceleration due to gravity is negative 9.8, and we're interested in the time. What we don't have and we don't care to find is our distance, so we choose the equation without it. Knowing that Vf is 0, we can just subtract Vi from both sides and then divide both sides by a, put our numbers in, which gives me 2.551, or 2.6 seconds to 2 significant figures. Calculate the time taken for the arrow to reach the height of the adventurer's knee. And so we just found the time for it to reach its maximum height, but now we need to find the time for it to fall. To do this, we can find its upwards distance, and then add on the 5 meters it is above the adventurer's knee, We'll then use a kinematic equation to find the time, and then add on the time it took to reach the maximum height. And so to find the upwards distance, I'm going to use this equation here. Vf is 0, so we can just subtract Vi squared from both sides and then divide by 2a. Put our numbers in, gives me 31.89 meters. The total fall distance is going to be this number plus the 5 meters that our bow is above the knee, which gives me 36.89 meters. To find the time to fall, we can use the equation d equals Vit plus half at squared, where because we're falling from our maximum height, our initial velocity is 0, so this equation just becomes d equals half at squared. We can rearrange this for time by doubling both sides, dividing them by a, and then square rooting. Putting our numbers in gives me 2.744 seconds. Our total time is therefore the time that we found in part B, plus this new time to fall, which gives me 5.295, or 5.3 seconds to two significant figures. Calculate the horizontal distance the bandit needs to shoot from to strike the adventurer's knee. We know that our horizontal velocity is 43.30 meters per second because we found it in part A. We know our total time, and so we can relate these to distance using our V equals d over t, multiplying both sides by t to solve for d. Putting in our numbers gives me 229.3 or 230 meters to two significant figures. Calculate the speed of the arrow as it strikes the adventurer's knee. To find our total final velocity, this is going to be the hypotenuse of our horizontal and vertical final velocities. We know our final horizontal velocity because it's the same as our initial. To find our final vertical velocity, we can use this equation here, where we are analyzing the arrow as it falls from its maximum height. In this case, Vi is 0, so we get At, our acceleration is negative 9.8, and the time that it takes to fall is 2.744, which gives us negative 26.89 meters per second. Putting this number in gives us 50.97 or 51 meters per second to two significant figures. Question 8. While admiring the view from the top of the Sky Tower in Auckland, a physics professor sneezes and spits his false teeth off the observation deck. The Sky Tower is 328 meters tall. Assume the false teeth are ejected horizontally with an initial speed of 15 meters per second. Calculate the time it takes for the false teeth to fall to the ground. They fall a distance of 328 meters. Our initial vertical velocity is 0 because they're ejected horizontally. Our acceleration downwards is negative 9.8 meters per second, and we're trying to find the time. The thing we don't have and don't care to find is the final velocity, and so we choose the equation without it. Vi is 0, so this becomes half at squared. We can solve this for time by doubling both sides, dividing by a and square rooting. Putting our numbers in gives me 8.182 or 8.2 seconds to two significant figures. Calculate the distance from the base of the tower that the false teeth land. We're analyzing the horizontal motion, so we can use the V equals d over t equation because there's no horizontal acceleration. Solving this for d by multiplying both sides by t, putting in the initial speed we're given in the question, and the time that we just found, gives us 122.7 or 120 meters to two significant figures. Calculate the final speed of the false teeth just before they hit the ground. To find our total velocity, this is going to be the hypotenuse of our vertical and horizontal, where we know our horizontal because it doesn't change, but we need to find our final vertical. To do so, we can use this equation here. Vi is 0, so this becomes At. Putting in our numbers gives me 80.18 meters per second. Putting this in gives us 81.57 or 82 meters per second to two significant figures. Force. Question 1. Calculate the size and direction of the net force on the objects below. State the direction as a word, for example, left, right, up, or down. We have a dog with a force of 20 newtons to the left and 5 newtons to the right. 20 is bigger than 5, so our force is towards the left. and 20 minus 5 is 15, so our force is 15 newtons. We have a remote controlled car with an upwards and downwards force of 3 newtons. These forces balance, so they don't contribute to the net force. We also have a force of 7 newtons to the right and 2 newtons to the left. 7 is bigger than 2, so our force is toward the right, and 7 minus 2 is 5 newtons. We have a hot air balloon with a force of 8,500 newtons upwards and 7,000 newtons downwards. 8,500 is larger than 7,000, so our net force is upwards, and 8,500 minus 7,000 is 1,500 newtons. Question 2. Calculate the size and direction of the net force on the objects below. Give the angle relative to the horizontal. We have a boat with an upwards force of 450 and a force towards the left of 210. Adding these two vectors together gives us our total force here, which is the hypotenuse of this right-angled triangle. To find the hypotenuse, we just use Pythagoras, which gives me 496.6, or 500 newtons to two significant figures. To find the angle, we can use the fact that we have the opposite and adjacent, and use the relationship that tan of the angle is our opposite 450 divided by our adjacent 210. Rearranging that for our angle by taking the inverse tan of both sides gives me 64.98, or 65 degrees to two significant figures. We have a fighter jet with an upwards force of 7,500, downwards of 8,900, a force of 1,330 to the left, and 450 to the right. That gives us an unbalanced force of 8,800 towards the left, and vertically 1,400 newtons downwards. We can once again calculate our total force by using Pythagoras, which gives me 1,654, or 1,700 newtons to two significant figures. Once again, to find our angle, we can use the fact that this is our opposite and this is our adjacent. Tan of the angle is our opposite divided by our adjacent. Solving this by taking the inverse tan of both sides gives me 57.85 degrees, or 58 degrees to two significant figures. Question 3. Calculate the force experienced by the following. A 70 kilogram bungee jumper accelerates downwards at 8.3 meters per second. Force is mass times acceleration. Putting those numbers in gives us 581, or 580 newtons to two significant figures. A 1,200 kilogram police car accelerates at 2.0 meters per second. Once again, F is equal to ma. Putting our numbers in gives me 2,400 newtons. Question 4. Calculate the mass of the following. A lunar astronaut drops a hammer. It accelerates at 2.0 meters per second with a force of 1.6 newtons. Solving F equals ma for the mass gives us force divided by acceleration. Putting these numbers in gives me 0.80 kilograms. A train's engine exerts a force of 160 kilonewtons to accelerate at 4.0 meters per second along a track. Once again, mass is force divided by acceleration. Putting in our numbers, we're at 160 kilonewtons is 160,000 newtons, which gives me 40,000 kilograms. Question 5. Calculate the acceleration of the following. A 2 kilogram remote controlled plane generates a thrust of 150 newtons. Taking F equals ma and solving it for the acceleration gives us force divided by the mass. Putting these numbers in gives me 75 meters per second. A parachute exerts a force of 400 newtons on a descending 80 kilogram skydiver. Once again, acceleration is force divided by mass. Putting these numbers in gives me 5.0 meters per second. Question 6. Frank pushes a lawnmower with a force of 110 newtons at an angle of 60 degrees to the horizontal. Calculate the component of force pushing the lawnmower forward. If Frank is exerting this force at an angle of 60 degrees at the horizontal, because the lawnmower is moving horizontally, we're interested in the horizontal component of this force. This gives us a right-angled triangle, where 110 is our hypotenuse, and the component that we're trying to find is our adjacent. We can therefore use the ka relationship in SOHCAHTOA, which is that cosine of our angle, which is 60 degrees, is equal to the force we're trying to find, divided by the hypotenuse, which is 110. Multiplying both sides by 110 gives us this equation here, which equals 55 newtons. Frank reduces the angle of the handle to 50 degrees. Calculate the force Frank must apply to push the lawnmower forward at the same speed. For the lawnmower to be going at the same speed, it still needs to have 55 newtons pushing it forwards. We therefore now have the angle, and we're trying to find the total force. This is once again our right angle triangle, where this is still the adjacent, but we're now trying to find the hypotenuse. So we can once again use our ka relationship in SOHCAHTOA, where cosine of our angle is our adjacent 55, divided by the force that we're trying to find, our hypotenuse. Multiplying both sides by f gives us this equation here. Dividing both sides by cosine 50 solves for our force, which gives me 85.56 or 86 newtons to two significant figures. Question 7. A 120 kilogram boat's propeller generates 230 newtons of force. The boat accelerates at 1.6 meters per second. Calculate the size of the force opposing its motion. The force opposing the motion is going to be the component of force that isn't providing the acceleration. So it's going to be our total force of 230 minus the force providing our acceleration, which is mass times acceleration, or 120 times 1.6. That gives us 38 newtons. Describe the motion of the boat if the propeller was slowed to equal the opposing force. If the opposing force is equal to the force of the propeller, the forces will balance, and the net force and net acceleration will equal 0. As the net acceleration is 0, the velocity of the boat will remain constant. Question 8. Abby the astronaut and her spacesuit have a combined mass of 150 kilograms. Calculate the gravitational force she would experience on these bodies here. Gravitational force is mass times the acceleration due to gravity. Our mass is the same in all cases, 150. However, our gravitational acceleration is different for each body. For Earth, that gives us 1,470 or 1,500 newtons to two significant figures. On the Moon, that gives us 240 newtons. And on Jupiter, that gives us 3,750 or 3,800 newtons to two significant figures. Question 9. The Electron rocket has a mass of 12,000 kilograms and experiences an upwards thrust force of 260 kilonewtons on takeoff. Calculate the gravitational force on the rocket while it's on the ground. The gravitational force is just mass times gravity. Putting in those numbers gives us 117,600 or 120,000 newtons to two significant figures. Calculate the resultant force on the rocket as it takes off. Our resultant force is going to be the sum of the up force and the down force, where we'll make the downwards gravitational force negative and the upwards thrust force positive. And so adding our 260 kilonewtons and negative 117,600 gives us 142,400 or 140,000 newtons to two significant figures. Use the equation F equals ma to explain how the acceleration of the rocket would change if it was manufactured from a lighter material. Assume the upwards thrust force remains the same. If the rocket was made from lighter material, its mass would be less. If the mass of the rocket decreases, while the upwards thrust force remains the same, since force is equal to mass times acceleration, and the force is the same and the mass has decreased, the acceleration of the rocket will increase. Question 10. A rescue helicopter winches up an injured hiker. The hiker and stretcher have a combined mass of 120 kilograms. They accelerate towards the helicopter at 0.9 meters per second. Calculate the tension force on the rope. The tension of the rope is going to be due to the hiker's gravitational force and the force pulling the hiker upwards, which is mass times acceleration. That gives us 1,284 or 1,300 newtons to two significant figures. What should the helicopter pilot do to remain at the same height as the hiker is winched up? The helicopter will experience an additional downwards force. To remain at the same height, the pilot must increase the upwards lift force on the helicopter. This will make sure that the downwards force from pulling the hiker up is counteracted by an increased lift force, such that the net force would be 0, and the helicopter would remain at the same height. Question 11. In a theme park ride called the Slingshot, riders are launched upwards by springs attached to either side of their seat. Before the launch, the seat is fixed to the ground and the springs are tensioned. Draw a force diagram showing the forces on the riders before they are launched. We will have forces from each spring, which are pulling them up in these directions here. The riders will be experiencing a downwards force of gravity and a downwards force from the hook keeping them attached to the ground. An important detail is that the net force on the riders must be 0. That means that the upwards and downwards force is equal, as we see the total downwards force here is equal to the force of the spring upwards, multiplied by 2 because we have 2, and that the length of these two is about the same. We also know that the horizontal forces must equal, which we can see because these spring forces point in opposite directions and have equal and opposite horizontal components. Draw a force diagram showing the forces on the riders the moment the chair is released. The moment the chair is released, our springs will still momentarily have the same amount of extension, and so the forces they provide will still be the same. The mass of our riders will not have changed, and so their gravitational force will be the same as well. The only thing missing is the force from our hook keeping the riders attached to the ground. The riders slow to a stop in the air. Draw a force diagram showing how the forces balance. As before, we have the same gravitational force. The only two other forces are the forces from our springs, which must be drawn such that the forces balance. So once again, our left and right horizontal components balance, and our downwards gravitational force is cancelled out by the upwards component of our two spring forces. Question 12. As an elevator moves, the occupants at different times feel heavier, lighter, and no different than standing still. Compare the forces acting on the occupants while the elevator is stationary. The occupants experience an upward support force from the elevator floor and a downwards gravitational force. When the elevator is stationary, these forces are balanced. That is to say that in our elevator, regardless of what the elevator is doing, we're going to have our downwards gravitational force, and if the elevator is stationary, we're going to have an equal and opposite support force, such that these forces cancel out, and the net force is 0. Compare the forces on the occupants as the elevator accelerates upward. As the elevator accelerates upwards, the downwards gravitational force does not change, however the upward support force increases. So that if our elevator is accelerating upwards, we must have a net upwards force, which means that our support force must have grown larger. Compare the forces on the occupants as the elevator moves upward at a constant speed. If the elevator moves at a constant speed, the net acceleration and net force must be 0. Therefore, the downward gravitational force and upward support force must be equal. And so, as with the case where our elevator was stationary, our forces must be balanced. Compare the forces on the occupants as the elevator decelerates to a stop. As the elevator decelerates, the net acceleration and net force must be downward. Therefore, the upward support force must have decreased in size and is now smaller than the downward gravitational force, meaning that our support force is smaller than it was before, such that our gravitational force is larger, meaning that we have a net force downwards, and because the net force is in the opposite direction to our elevator's velocity, the elevator must be decreasing in speed, or in other words, decelerating. Discuss how these forces would change if the elevator cable suddenly snapped. If the cable suddenly snapped, the elevator would no longer apply an upward support force to the occupants. The only force acting upon them would be the downwards gravitational force, which would cause them to accelerate downwards at the same rate as the elevator around them. And so, with no support force, the elevator and the occupants will accelerate downwards due to gravity at the same rate. Question 13. NASA's Artemis program plans to establish a crewed moon base by 2035. Its launch vehicle, the Space Launch System SLS, produces a constant thrust force by ejecting fuel downwards at a constant rate. Explain whether the acceleration of the SLS will remain constant as it ascends. As the Space Launch System ejects fuel, its mass will decrease. Because the thrust force remains constant, and F equals ma, as the mass decreases, the acceleration of the SLS must increase. Hooke's law. Question 1. Calculate the force required in the following situations. A spring with a spring constant of 80 newtons per meter is compressed by 0.15 meters. We know our spring constant is 80. We know our displacement is 0.15. We can use Hooke's law. Putting our numbers in gives us negative 12 newtons. Noting that what this negative sign does is make sure that the displacement and the force have the opposite sign, which indicates that they're in the opposite direction. A rubber band with a spring constant of 2.4 newtons per meter is stretched by 1.2 meters. Our spring constant is 2.4, our displacement is 1.2. Once again, using Hooke's law, putting our numbers in, gives us negative 2.88 or negative 2.9 newtons to two significant figures. Question 2. Calculate the spring constant in the following situations. A basketball is compressed by 0.025 meters and the force applied is 40 newtons. Our force is 40 and our displacement is 0.025 meters. Because these are in the opposite direction, we need to make one of them negative. It doesn't matter which one you choose. In this case, I'm going to choose the force. Solving Hooke's law for k gives us negative F over x. Putting our numbers in gives me 1600 newtons per meter. A slingshot is stretched by 0.5 meters and the force applied is 150 newtons. We have our force and our displacement. Once again, I'm going to make the force negative. Using our equation solved for k and putting our numbers in gives me 300 newtons per meter. Question 3. Calculate the displacement in the following situations. An elastic band with a spring constant of 150 newtons per meter is subjected to a force of 45 newtons. Our force is 45. Our spring constant is 150. Solving Hooke's law for x by dividing both sides by k. Putting our numbers in gives me negative 0.3 meters. A trampoline with a spring constant of 60 newtons per meter is compressed with a force of 30 newtons. Our force is 30, our spring constant is 60. Using our equation solved for x, putting our numbers in, gives me negative 0.5 meters. Question 4. A 12 kilogram box is suspended from two identical springs. Calculate the gravitational force on the box. Force is mass times gravity. We know the mass and we know the gravitational acceleration, which gives me 117.6 or 120 newtons to two significant figures. Calculate the vertical component of the force provided by each spring. Imagining our two springs applying forces in these directions, countering our gravitational force, we know that the vertical component of the force of these two springs must be equal to the downwards gravity. Because these springs are identical, the vertical component of just one of these springs is going to be half of the gravity force. So that is 117.6 divided by 2, which gives me 58.8 or 59 newtons to two significant figures. If the springs are angled at 50 degrees, calculate the total force that each spring provides. Imagining the force from one of our springs at an angle of 50 newtons, we know that this vertical component is 58.8. Because this is the opposite and this is the hypotenuse, we need to use the SO relationship in SOHCAHTOA, which is that sine of the angle is equal to the opposite, our 58.8, divided by our hypotenuse f, which is what we're trying to find. Solving this for our force, by swapping our sine 50 and our force, that gives me 76.76, or 77 newtons to two significant figures. The springs are extended by 47 centimeters. Calculate their spring constant. Our extension of 47 centimeters is 0.47 meters, and our force is 76.76, where we need to make one of these negative. It doesn't matter which one, I've chosen to make the displacement negative. Our force is negative kx, solving that for k by dividing both sides by x, putting our numbers in, gives me 163.3 or 160 newtons per meter to two significant figures. Question 5. A child with a mass of 35 kilograms jumps onto a trampoline. The trampoline acts like a spring with a spring constant of 1200 newtons per meter. Calculate the force exerted by the trampoline when it's compressed by 0.3 meters. Force is negative kx, but since we're only concerned about the magnitude, we can just use kx. Putting these numbers in gives me 360 newtons. Calculate the net force on the child. The net force on our child is the trampoline force that we just found, minus the force of gravity. The reason it's minusing is because it's in the opposite direction. The force of gravity is just mass times gravity. Putting those numbers in gives me 343 newtons. Putting our forces into our final equation gives me 17 newtons. Calculate the initial acceleration of the child as the trampoline pushes them back up. For this, we can use F equals ma. Solving for our acceleration gives me F over m. Putting our numbers in gives us 0.4857 or 0.49 meters per second to two significant figures. The child bounces again, causing the trampoline to compress by twice as far. Discuss how this affects the force experienced by the child. Since F equals kx and the spring constant of the trampoline does not change, doubling the compression of the trampoline, which is to say doubling x, is going to double the force that the trampoline applies to the child. The gravitational force of 343 newtons on the child does not change. The force from the trampoline doubles from 360 to 720. The net force therefore increases from 17 newtons to 377 newtons, which we find by performing the same calculation here, except by doubling our 360 to 720. Question 6. A car is being towed by a truck using a cable that stretches like a spring. The spring constant of the cable is 1500 newtons per meter. Calculate the force exerted by the cable on the car when it is stretched by 0.15 meters. We know our spring constant, we know our x, we know Hooke's law. Putting our numbers in gives me 225 or 230 newtons to two significant figures. How does this force compare with the force the cable exerts on the tow truck? The forces the cable exerts on the car and tow truck are equal and opposite. This is due to Newton's third law. Question 7. Billy attempts to calculate the spring constant. He substitutes that the force is equal to 10 newtons and the displacement is 0.5 meters into the equation k equals negative f over x and gets negative 20 newtons per meter. Billy is confused as he knows k should always be positive. Explain what Billy has done wrong and what he should do to fix this. Displacement and force are in opposite directions, so one must be negative. Making either negative will cancel out the existing negative in the equation and give a positive value. It doesn't matter which one you choose to be negative, choosing either one will cancel out this negative here. Question 8. Marco sits on a motorbike. The motorbike has two suspension springs which compress under his weight. When his twin brother Lionel of the same mass also climbs aboard, how will the distance the springs compress change? Doubling the mass on the springs doubles the downwards force on the springs. Because the spring constant doesn't change and the force is negative kx, doubling the force doubles the distance the springs compress. That is to say, if our spring constant doesn't change and we double the force, our x must double as well. Circular motion. Question 1. Complete the table below. We have a list of planets, their orbital periods, their orbital radius, and we need to calculate their distance per orbit and their orbital speed. The distance per orbit is just the circumference of the circle that they trace, which is 2 pi times the radius. The orbital speed is distance over time, where we can use the distance per orbit divided by the orbital period. We know the distances per orbit, and although we know our orbital periods, we need these values in seconds. We can convert 365 days by first multiplying it by 24 hours, and then 60 minutes, and finally 60 seconds. For 88 days, we do exactly the same. For our values in years, however, we also need to multiply this by the amount of days in a year, which is 365. Putting those numbers in gives us our orbital speeds. Question 2. A satellite orbits Earth every 90 minutes at an altitude of 400 kilometers. The radius of Earth is 6,400 kilometers. Calculate the radius of the satellite's motion. If we imagine our Earth and our satellite above, the radius of our motion is going to be the radius of the Earth plus the altitude of the satellite. Putting those numbers in gives me 6,800 kilometers, or 6.8 times 10 to the 6 meters. Calculate the distance the satellite travels for each orbit. This is just our 2 pi r. Putting in our radius gives us 4.273 times 10 to the 7, or 4.3 times 10 to the 7 meters to two significant figures. Calculate the orbital period of the satellite in seconds. We have our orbital period in minutes. To get it into seconds, we just need to multiply it by 60, which gives me 5,400 seconds. Calculate the velocity of the satellite. Velocity is distance over time, where we can use the distance for one orbit divided by the time for one orbit, which gives me 7,913, or 8,000 meters per second to two significant figures. Question 3. The Sky Tower's revolving restaurant completes one full revolution every hour. Calculate the restaurant's rotational period in seconds. We have our orbital period of an hour, in which there is 3,600 seconds. 60 minutes times 60 seconds. Calculate the length of the path traveled by a diner 5.8 meters from the center of the tower. The length of the path is going to be the circumference, which is 2 pi times the radius, where the radius is our 5.8 meters, which gives me 36.44, or 36 meters to two significant figures. Calculate the tangential velocity of the diner. Velocity is distance over time, where we can use the distance in one rotation, which we found in part B, divided by the time for one rotation, which we found in part A. That gives me 0.01012, or 0.010 meters per second to two significant figures. Question 4. The tip of a lawnmower blade rotates 2,800 times per minute. The length of the blade, measured from the center of rotation to the tip, is 0.5 meters. Calculate the distance traveled by the tip of the blade during one full revolution. This distance is the circumference of our circle, which we can find with 2 pi r, where our radius is 0.5, which gives us 3.142, or 3.1 meters to two significant figures. Calculate the velocity of the tip of the lawnmower blade. Our velocity is our distance over time, where we can use the distance for one full revolution that we found in part A, and we know that the blade rotates 2,800 times per minute, and so to find our time, we take our 1 minute or 60 seconds and divide that into 2,800, which gives us 0.02143 seconds. Putting that number in gives us 146.6, or 150 meters per second to two significant figures. Question 5. The pulsar PSR J174824446AD is observed to rotate 716 revolutions per second. The pulsar has an estimated radius of 16 kilometers. Calculate the rotational period of the pulsar. We know that in 1 second we have 716 revolutions, so to find our period, we divide 1 second into 716, which gives us 0.001397, or 0.0014 seconds to two significant figures. Calculate the distance a point on the surface travels during one full revolution. For this, we need to find the circumference, which is 2 pi r. Putting our radius in gives me 1.005 times 10 to the 5, or 1.0 times 10 to the 5 meters to two significant figures. Calculate the velocity at the surface of the pulsar. We calculated our circumference in the last question, Our velocity is our distance over our time, gives me 7.194 times 10 to the 7, or 7.2 times 10 to the 7 meters per second to two significant figures. Centripetal acceleration. Question 1. Write an equation for r in terms of AC, v, and m. For this, we need to take our equation here, and we can just swap these two values around, which gives me v squared over AC. Question 2. Write an equation for m in terms of FC, v, and r. For this, we take our equation here, multiply both sides by r, and divide both sides by v squared, which gives us FCr divided by v squared. Question 3. Write an equation for v in terms of AC, r, and m. Taking this equation here, we can first of all solve for v squared by multiplying both sides by r and dividing by m, and then square rooting both sides. Question 4. Calculate the centripetal force of the following. A 1200 kilogram car takes a turn around a bend with a radius of 30 meters at a speed of 18 meters per second. Using our centripetal force equation, putting in our mass, our radius, and our velocity, gives us 12,960 or 13,000 newtons to two significant figures. The Moon orbits Earth at an average speed of 100 meters per second and orbital radius of 380,000 kilometers. The Moon has a mass of 7.4 times 10 to the 22 kilograms. We know our radius is 380,000 kilometers, which is 3.8 times 10 to the 8 meters. Taking our centripetal force equation and putting all of our values in gives me 1.947 times 10 to the 20, or 1.9 times 10 to the 20 newtons to two significant figures. Question 5. Calculate the velocity of the following. An Olympic hammer thrower applies a force of 1500 newtons to spin a 7.3 kilogram hammer in a circle with a 2 meter radius. For this, we can take our solved velocity equation, put in our numbers, which gives me 20.27 or 20 meters per second to two significant figures. A 500 kilogram roller coaster car reaches the top of a vertical loop with a radius of 15 meters. The centripetal force acting on the car is 3000 newtons. Once again, taking our velocity equation that we solved for on the last page, putting in our numbers gives me 9.487 or 9.5 meters per second to two significant figures. Question 6. Calculate the radius of the following. An 800 kilogram satellite orbits Earth with a speed of 7,800 meters per second and experiences a gravitational force of 6,500 newtons. For this, we can take our centripetal force equation, we can solve it for r by swapping our FC and our r around, putting our numbers in, gives me 7.488 times 10 to the 6, or 7.5 times 10 to the 6 meters to two significant figures. A 50 kilogram thrill seeker on a merry-go-round moves at 6.5 meters per second and experiences a centripetal force of 300 newtons. Using our radius equation that we found above, putting in our numbers, gives me 7.042 or 7.0 meters to two significant figures. Question 7. A car travels at 15 meters per second around a flat circular track with a radius of 30 meters. Add labeled arrows to the diagram below to show the direction of the car's centripetal force and velocity. Centripetal force is always towards the center of the circular motion, where centripetal literally translates to center seeking. And furthermore, during circular motion, the velocity vector is always tangential to the circle, or in other words, at right angles to the centripetal force. What provides the centripetal force on the car? This is the friction force between the car's tires and the road surface. This is the case when we have a flat circular track. If instead our road was instead banked, then a portion of our centripetal force could come from the reaction force, because it would have a component towards the center of the circle. Explain how the car can be moving at a constant speed but still be accelerating. Acceleration occurs if the velocity of an object changes. Velocity is a vector, so has both size and direction. While the size of the velocity does not change, the direction does. since as our car goes around the bend, the centripetal force is always going to be changing towards the center of the circle. Therefore, the velocity is changing and the car is accelerating. Calculate the centripetal acceleration of the car. We know that centripetal acceleration is v squared over r. We know the velocity is 15 and that the radius is 30, which gives us 7.5 meters per second. How would this force need to change if the car repeated the turn at the same speed but with more passengers? If the car repeated the turn with more passengers, the mass of the car will be greater. Since F equals mv squared over r, and the speed is the same, since we were told it was the same, increasing the mass will increase the required centripetal force. That is to say that if the radius and the speed is the same, an increase in the mass must result in an increase in the force. The car hits a patch of ice and loses friction with the road. Explain how this affects the motion of the car. The centripetal force on the car is provided by its friction with the road. If the car loses friction, it loses its centripetal force and its centripetal acceleration. Its velocity will therefore stop changing direction, since the thing causing it to change direction is the centripetal acceleration, and the car will move with the tangential velocity it had at the moment it lost friction. So if our car lost friction at this point here, because it would no longer have this centripetal force changing the car's direction, it will continue with this velocity, and as far as the universe cares, it's just an object with velocity, with no memory that it ever had centripetal acceleration. Question 8. In 2024, Earth captured the small asteroid 2024 PT5 for 57 days. Its orbit around Earth can be estimated as circular, with a radius of 650,000 kilometers and a velocity of 10 kilometers per second. Calculate the centripetal acceleration of the asteroid. We know our velocity of 10 kilometers per second is 10,000 meters per second, and we know that our radius of 650,000 kilometers is 6.5 times 10 to the 8 meters. Knowing our centripetal acceleration equation and putting these numbers in gives me 0.1538 or 0.15 meters per second to two significant figures. If the mass of 2024 PT5 is 1.3 times 10 to the 6 kilograms, calculate the centripetal force required to keep it in this orbit. We know that force is mass times acceleration, and so we just multiply the acceleration we found in the last question by the mass we were just given. That gives me 199,900 or 200,000 newtons to two significant figures. Alternatively, you could use the force equation, mv squared over r, which amounts to exactly the same thing. What provides the centripetal force? This is the gravitational force from the Earth. If 2024 PT5 were to orbit Earth at the same speed, but at a larger orbital radius, how would the required centripetal force need to change? If the orbital radius increased while the speed remained the same, since F equals mv squared over r, the centripetal force would need to decrease. Torque. Question 1. Calculate the torque produced in the diagrams below. We have a wrench, upon which there is a 25 Newton force, at a distance of 10 centimeters away from its center of rotation. Our distance of 10 centimeters is 0.1 meters, and we know that torque is force times distance. Putting these numbers in gives us 2.5 Newton meters. We have a wheelbarrow, upon which there is a 30 Newton force at a distance of 1.3 meters. Once again, torque is force times distance. Putting these numbers in gives us 39 Newton meters. We have a person weighing 72 kilograms standing on a diving board 1.1 meters from the pivot point. In this question, our force is the gravitational force, which is mass times the acceleration due to gravity, which gives us 710 newtons. Torque is force times distance. Putting these numbers in gives me 780 Newton meters to two significant figures. We have a crane, which is lifting a 1200 kilogram load, a distance of 25 meters away from the pivot point. Once again, our force is gravitational, so is mass times the acceleration due to gravity. Putting those numbers in gives me 12,000 newtons. Torque is force times distance. Putting these numbers in gives me 300,000 Newton meters. Question 2. Explain why a longer wrench requires less effort to untighten a bolt. The torque produced is described by the equation torque is force times distance. Using a longer wrench increases the distance. Therefore, to produce the same amount of torque, a smaller force is required. And so looking at our equation, if we have the same amount of torque, if we increase the distance that we're applying the force, we can see that our force will decrease. Question 3. Calculate the net torque in the situations below. Here we have a frisbee with rockets attached, one applying 4 Newton meters of torque and the other applying 5. These torques are in the same direction, and so they add together to give us 9 Newton meter. And by same direction, I mean that they are both counterclockwise. Here we have a steering wheel, one hand providing 11 Newton meters of torque, and the other applying 15. Once again, both of these torques are in the same direction, in this case clockwise, and so the torques add together to give us 26 Newton meters. Here we have 2 people on a seesaw, one applying 920 Newton meters of torque and the other applying 730. These torques are in the opposite directions, this one being counterclockwise and this one being clockwise. The torques therefore subtract and we get 190 Newton meters. And now just to note, I made the decision to make this one positive and this one negative. If I had done this the other way around, then I would have had 730 minus 920. That would have given me negative 190, which would also be totally fine. Question 4. A 12 kilogram uniform plank is placed on a pivot. Calculate the net torque in the situations shown below. We have our plank, which is 2 meters long, and we have a pivot, which is 0.5 meters from one end. Because the gravitational force from the weight of our plank acts from the middle of the plank, it must be 1 meter from the end, which means that the distance to our pivot is 0.5 meters. The size of our force, because it's gravitational, is just mass times gravity, putting these numbers in, gives me 117.6 newtons. To find the torque, that is force times distance, putting these numbers in, gives me 58.8 or 59 Newton meters to 2 significant figures. For B, we once again have our 2 meter plank, however now our pivot is placed 1.2 meters from this end here. We once again know our force of gravity acts from the middle of the plank, which is once again 1 meter from the end. That means the distance to our pivot must be the remaining 0.2 meters. Knowing that torque is force times distance, using the force that we calculated here, since our mass is still the same, gives us 23.52 or 24 Newton meters to 2 significant figures. And once again we have the same plank. However, now our pivot is placed in the middle, 1 meter from the end. In this case, if we go torque is equal to force times distance, although there is still a gravitational force, because it acts at the pivot, its distance from the pivot is 0, and therefore the torque that it exerts is also 0. Single pivots. Question 1. Calculate the unknown value in the diagrams below. We have a plank on a pivot balanced in the middle. We have a mass exerting 10 newtons, which is 0.5 meters from the pivot, and we have a mass that is unknown on the other side, which is 1.2 meters from the pivot. Calculate the unknown force in the diagrams below. Ignore the mass of the plank. Because the plank is in equilibrium, we know that the clockwise and counterclockwise torques balance. Our clockwise torque is provided by this mass here, and our counterclockwise torque is provided by this one. We know that torque is force times distance, and so our purple mass is 1.2 meters, with the force that we're trying to find, and our 10 Newton mass is 0.75 meters. Rearranging this for force by dividing both sides by 1.2 gives me 6.25 or 6.3 newtons to 2 significant figures. For B, we have the same plank on a pivot balanced about the middle. On one side we have 15 newtons at a distance of 1 meter, and on the other side we have an unknown force 0.6 meters from the pivot. Once again, our clockwise and counterclockwise torques balance. This one here is our counterclockwise, and this one here is our clockwise. Once again, the torque is the force we're trying to find, multiplied by the distance it is from the pivot, 0.6. And on the other side we do the same, where our numbers are 15 and 1. Rearranging this for force by dividing both sides by 0.6 gives me 25 newtons. For part C, we have our same plank balanced on our pivot, a 5 Newton mass on one side, a distance of 1.6 meters from the pivot, and a 10 Newton mass on the other side, which is an unknown distance. Once again, we know that the clockwise torque must equal the counterclockwise, where this once again is our clockwise and this is our counterclockwise. For our clockwise, we know that the force is 10, and this time we don't know the distance. On the other side, we know both the force and the distance. Rearranging this for distance by dividing both sides by 10 gives me 0.8 meters. For part D, once again we have our pivot with 18 newtons, a distance of 1.2 meters on one side, and 12 newtons, an unknown distance, on the other. We know that the clockwise and counterclockwise torques balance, where this one is our counterclockwise and this one is our clockwise. Torque is our force of 12 times our unknown distance, and on the other side our known force and our known distance. Rearranging this for distance by dividing both sides by 12 gives me 1.8 meters. Question 2. Calculate the unknown values in the diagrams below. We have our plank balanced at the middle on a pivot, a 10 Newton mass 1.5 meters from the pivot, another 10 Newton mass on the other side, this one 0.7 meters from the pivot, and a 5 Newton mass which is an unknown distance from the pivot. Knowing that the plank is in equilibrium, we know that our clockwise torque equals our counterclockwise, where this is our counterclockwise, so we can substitute its force times its distance, and these ones are our clockwise. So we can substitute their forces times their distances, where we have our D, which is our unknown distance. Solving this for D by first subtracting 10 times 0.7 from both sides, and then dividing both sides by 5, we get 1.6 meters. For section B, we have a 5 Newton mass 0.6 meters from the pivot, a 1 Newton mass on the other side 1.2 meters from the pivot, and a third unknown mass, which is 0.6 meters from the pivot. The system is in equilibrium, so our clockwise and counterclockwise torques equal. Our counterclockwise torque is from this mass here, so we substitute its force times its distance, and our clockwise torques are from these masses here, so we substitute their forces times their distances. Solving for F, our unknown force, by first subtracting 1 times 1.2 from both sides, and then dividing both sides by 0.6, we get 3.0 newtons. For section C, we have a 12 Newton mass in unknown distance from the pivot, a 2 Newton mass on the other side, a distance of 1.5 meters from the pivot, and an 8 Newton mass, a distance of 0.9 meters from the pivot. Our clockwise and counterclockwise torques must equal because the system is in equilibrium. Our counterclockwise torque is this one here, so we substitute its force times its distance, which is the unknown we're trying to find, and our clockwise torques are from these masses here, so we substitute their forces times their distances. Solving for distance by dividing both sides by 12 gives us 0.85 meters. Question 3. A pirate ship navigator, caught writing distances without units, is sentenced to walk the plank. The 6-meter plank pivots at the edge of the ship, half over the water and half on the deck. A 120 kilogram treasure chest counterbalances the 76 kilogram navigator. As the navigator reaches the end of the plank, calculate the distance from the pivot the treasure chest must be placed to ensure it doesn't tip. To start with, we can find the force from the navigator and the force from the chest, knowing that these are gravitational forces, and we just need to multiply their masses by the acceleration due to gravity, which gives me 744.8 and 1176 newtons. For our plank not to tip, our system must be in equilibrium, and so our torques must balance. Where our chest provides the clockwise torque, so we substitute in its force times its distance that we're trying to find, and our navigator produces the counterclockwise torque, so we substitute in their distance times their force. Solving for our distance by dividing both sides by the force from the chest, putting in these numbers, gives me 1.9 meters. A spaceship is equipped with 2 thrusters, positioned 3.2 meters either side of the ship's center of mass, as shown below. Each thruster propels the ship with a force of 1300 newtons. Calculate the torque produced by each thruster. Torque is force times distance. We know the force, and we know the distance from the center, which gives us 4,160 or 4,200 Newton meters to 2 significant figures. One thruster malfunctions, causing it to produce only 700 newtons of force. Calculate the resulting torque about the ship's center of mass. The torque now produced by our bad thruster is its force times its distance, where its force has decreased to 700, while its distance remains the same. That gives us 2,240. Subtracting this from the torque produced by our other thruster, which is still going to be producing our original torque, gives me 1,920 or 1,900 Newton meters to 2 significant figures. The working thruster is able to be moved closer to the ship's center of mass. Calculate the distance it should be moved for it to balance the malfunctioning thruster. If the thruster's torques are balanced, then they must be equal. We know the torque from our bad thruster, we found it in the last section, and we know the torque from our good thruster is going to be its force of 1300 multiplied by its distance that we want to find. Solving for distance by dividing both sides by 1300 gives me 1.723 meters. To find the distance it needs to be moved, we find the difference between its original distance and its new distance that we just calculated. This is 1.477 or 1.5 meters to 2 significant figures. Double pivots. Question 1. Calculate the force provided by the supports indicated with the question mark symbol. For section A, we have a beam that is 2 meters long, supported by 2 pivots, where the value of the force provided by this one is what we're trying to find. We're given that the weight force of the beam is 10 newtons, and we have a 3 newton mass, which is 0.7 meters from the left pivot. To find the value of the force at this pivot, we can consider the torques about this pivot. We choose this pivot because when we form our equilibrium equation, the torque produced by this pivot will be 0 because its distance is 0. That suits us well because we don't have information about it. If we instead made this our pivot, then our equation would instead not feature the force from this pivot, which wouldn't be suitable because it's the force that we're trying to find. And so knowing the system is in equilibrium, we know that our torques must equal, where if this is our pivot, the torque here is counterclockwise, and the torques produced by our 3 and 10 Newton masses are going to be clockwise. Substituting in these forces multiplied by their distances, and solving for F by dividing both sides by 2 gives us 6.05 or 6.1 newtons to 2 significant figures. For section B, we now have a plank that is 20 meters long, has a gravitational force of 40 newtons, has 2 pivots. The left one has the force that we're trying to find. We have a 30 Newton mass, which is 13 meters from this end. In order to find the value of our force here, we need to make this end our pivot. Because the system is in equilibrium, our clockwise and counterclockwise torques will equal. Substituting in our forces times our distances, where we have our unknown force multiplied by the distance of 20, which is the distance this force is away from the pivot, the length of the beam. The 40 Newton weight force of the beam is a distance of half of our length of the beam away from the pivot, half of 20 is 10, and our 30 Newton mass is 13 meters from this end here, which means it must be 7 meters from the other end, which is its distance from the pivot. Solving for force by dividing both sides by 20 gives me 30.5 or 31 newtons to 2 significant figures. For section C, we have a 10 meter long beam with a gravitational force of 35 newtons in the middle, 2 pivots. The force from the left one is what we're trying to find. We have a 12 Newton mass, a distance of 2 meters from the left, and a 10 Newton mass, a distance of 4 meters from the right. To find the value of this force here, we need to make this our pivot. We know that the torques must balance about this pivot, where this is our only clockwise torque, so we substitute its force times its distance, and these are our counterclockwise torques. Our 12 Newton mass because it's a distance of 2 meters from this side, must be a distance of 8 from our pivot. The gravitational force from our beam acts in the middle, and so its distance is half of our 10 meters. Our 4 Newton mass is 4 meters from the pivot. Dividing both sides by 10 to solve for our force gives me 31.1, or 31 newtons to two significant figures. Section D has a 15 meter long beam with a gravitational force of 10 newtons in the middle. It has 2 pivots, and in this case we want to find the value of the forces acting at both. We have a 5 Newton mass 4 meters from the left, and an 8 Newton mass 3 meters from the right. I'm going to call the force from this pivot F1 and the force from this pivot F2, and we'll start by finding F1. To do so, I need to make this side my pivot, and we'll consider the torques about it. We know that these torques must balance, and that the only clockwise torque is going to be that from our F1. So we substitute in its force times its distance, and our counterclockwise torques are going to be from our gravitational forces, which are our 5 Newton mass, which, because it's 4 meters from the left, means it must be 11 meters from the right. Our 10 Newton weight force of the beam is going to be half of our 15 meters from the pivot, which is 7.5, and our 8 Newton mass is 3 meters from the pivot. Solving for our force by dividing both sides by 15 gives me 10.27, or 10 newtons to two significant figures. And now to find F2, we could repeat this same process, but with the other side being our pivot. A quicker way, however, is to make use of our second equilibrium condition, which is that our forces must be balanced. Specifically, our up forces must equal our down forces. Our upwards forces are from our pivots F1 and F2, and our downwards forces are our gravitational forces. Solving for F2 by subtracting F1 from both sides, substituting in the value of F1, gives us 12.73, or 13 newtons to two significant figures. Question 2. A 50 meter long bridge is shown below. The bridge has a mass of 1.5 times 10 to the 6 kilograms, and the two supports are 5 meters from each end. State the conditions for equilibrium. These are that the net force is 0, and that the net torque is 0. Alternatively, you could say that the net force and net torque are balanced. Determine the total downwards force on the bridge. The only downwards force is that from the mass of our bridge, which, because it's gravitational, we can find using mass times gravity. Putting in these numbers gives me 1.47 times 10 to the 7, or 1.5 times 10 to the 7 newtons to two significant figures. State the total upwards force on the bridge, and explain how you determined this. Because the bridge is in equilibrium, the net force on the bridge must be 0. This means the total upwards force must equal the total downwards force. The total upwards force is therefore 1.5 times 10 to the 7 newtons, the same as what we found here. Calculate the total clockwise torque about support A. We know that torque is force times distance, we know the force, and because we know the total length of the bridge is 50, if we take 5 meters away from each end, that means that the distance between the supports is 40. That means the distance from our support A to the middle must be half of this, or in other words, 20. That gives me 2.94 times 10 to the 8, or 2.9 times 10 to the 8 Newton meters. State the total counterclockwise torque on the bridge, and explain how you determined this. Because the bridge is in equilibrium, the net torque on the bridge must be 0. Given that this is one of our equilibrium conditions. This means the total clockwise torque must equal the total counterclockwise torque. The total counterclockwise torque is therefore 2.9 times 10 to the 8 Newton meters, the same as what we found in the last question. Question 3. An 80 kilogram patient on a 2.2 meter long stretcher is held stationary by a paramedic at each end. The stretcher has a mass of 11 kilograms. A paramedic at one end exerts a force of 580 newtons upwards. Calculate the force the other paramedic must exert. We're told that the stretcher is stationary, which means that it must be in equilibrium. That means we can make the statement that the up forces equal the down forces, where our upwards forces are the force from the paramedic that we're trying to find, plus the 580 newton force from the other paramedic. Our downwards forces are the weight forces of our patient and our stretcher. Solving this for our force by by subtracting 580 from both sides gives us 311.8 or 310 newtons to two significant figures. Calculate the distance of the patient's center of mass from the middle of the stretcher. Drawing our situation with all of our forces, where because we are told that the stretcher is 2.2 meters long, we know that our gravitational force from our stretcher must act 1.1 meters from the end. To find the distance to the patient's center of mass, we can choose this end as our pivot, and knowing that the stretcher is in equilibrium, recognize that that means that our clockwise and counterclockwise torques must equal. With this end as our pivot, our clockwise torques are from our two gravitational forces, so we can substitute their forces, which are their masses times gravity, and multiply that by their distances. Our only counterclockwise torque is from the paramedic at the end. They provide a force of 580 at the other end of the stretcher, which is 2.2 meters. We can solve this for D by subtracting 11 times 9.8 times 1.1 from both sides, and then dividing both sides by 80 times 9.8. That gives us 1.476, or 1.5 meters to two significant figures. Question 4. Christopher the tightrope walker balances by holding a 4-meter long pole. He positions his hands 0.3 meters either side of the middle of the pole. The mass of the pole is 12 kilograms. A 1.3 kilogram seagull lands 0.2 meters from the left end of the pole. Draw a diagram of the situation below with all the forces labelled. And so we have our pole, the upwards forces from our left and right hand, and the weight force of our pole acting from the middle. Calculate the force Christopher must provide with each hand to keep the pole balanced. We can start by finding our gravitational forces, which are just the masses times the acceleration due to gravity, which gives us 12.74 and 117.6 newtons. Next, I'm going to make F left our pivot in order to find F right. To help us work out the distances, I'm going to annotate on the diagram above. So we know that the length of this pole is 4 meters, and we know that each hand is 0.3 from the end. 0.3 plus 0.3 is 0.6. Subtracting that off our 4 meters gives us a separation between our hands of 3.4. And now we're making our F left our pivot. The middle of 3.4 is 1.7, and so we know that that is the distance to the middle of our pole, where the gravitational force of the pole acts. And we're told that our gull lands 1.2 meters from the end. 1.2 minus 0.3 gives us that it's 0.9 meters from F left. And so we know that for the pole to be balanced, it must be in equilibrium, which means that our counterclockwise and clockwise torques must equal. Our only counterclockwise torque is from F right, which is a distance of 3.4 away from our F left, our pivot. Our clockwise torques are from the weight of our gull, which is 0.9 from our pivot, and the weight force from our pole, which is 1.7 from our pivot. Solving this by dividing both sides by 3.4, putting our numbers in, gives me 62.17, or 62 newtons to two significant figures. And now to find the force from our left pole, we can make use of our other equilibrium condition, that the forces must balance. Specifically, that the up forces equal the down forces. Our up forces are the forces from each hand, and our down forces are the two gravitational forces. Solving this for F left by subtracting F right from both sides, putting our numbers in, gives me 68.17, or 68 newtons to two significant figures. Kinetic energy. Question 1. Write an equation for V in terms of EK and M. To solve for V squared, we can double both sides and divide by mass, and then finally take the square root of both sides. Question 2. Calculate the kinetic energy of the following. A 70 kilogram skateboarder coasting downhill at 4 meters per second, taking our kinetic energy equation, putting in our mass and our velocity, gives me 560 joules. A 0.12 kilogram wood pigeon flying at 10 meters per second through the forest, once again taking our kinetic energy equation, putting in our numbers, gives me 6.0 joules. Question 3. calculate the speed of the following. A 25 kilogram sheepdog running with 450 joules of kinetic energy, using our velocity equation that we found in question 1. Putting our energy and our mass in gives me 6.0 meters per second. A 75 kilogram surfboarder with 2,300 joules of kinetic energy while riding a wave. Once again, taking our velocity equation, putting in our numbers, gives me 7.832 or 7.8 meters per second to two significant figures. Question 4. Calculate the mass of the following. A kayaker paddling at 3.8 meters per second with 90 joules of kinetic energy. Taking our kinetic energy equation and solving it for mass by doubling both sides and dividing both sides by v squared, putting our numbers in, gives me 12.47 or 12 kilograms to two significant figures. A hiker's backpack sliding down a hillside at 5.1 meters per second with 50 joules of kinetic energy. We have our kinetic energy equation, once again solving it for mass by doubling both sides and dividing by v squared, putting our numbers in, gives me 3.845 or 3.8 kilograms to two significant figures. Question 5. An impatient driver is caught driving at 60 kilometers per hour in a 30 km per hour school zone. Calculate the kinetic energy of a 1300 kilogram car traveling at 30 km per hour. To take our 30 km per hour and convert it into meters per second, we just divide by 3.6. which gives me 8.333 meters per second. And now taking our kinetic energy equation, putting our numbers in, gives me 45,120 or 45,000 joules to two significant figures. Calculate the kinetic energy of a 1300 kilogram car traveling at 60 kilometers per hour. Once again, we can convert our kilometers per hour to meters per second by dividing by 3.6, which gives me 16.67 meters per second. Once again, using our kinetic energy equation and putting our numbers in, gives me 180,600 or 180,000 joules to two significant figures. Discuss how increasing the speed of the car affects its kinetic energy. Because EK is equal to half mv squared, kinetic energy is proportional to speed squared. Therefore, in the example above, a doubling of the car's speed results in a quadrupling of the car's kinetic energy. Putting this more mathematically, if we have our EK equals half mv squared, and we were to replace our v with 2v, expanding these brackets out would give us half m2 squared v squared. 2 squared is 4, which we can bring out the front, and we see that we get 4 times half mv squared, which is 4 times our original kinetic energy. Question 6. Asteroid 1950 DA has a mass of 2.7 times 10 to the 12 kilograms and is estimated to have a 1 in 34,000 chance of impacting Earth in 2880. Its estimated speed at impact is 18,000 meters per second, which is 64,000 kilometers per hour. Calculate the time it would take the asteroid to travel 1,000 kilometers through our atmosphere at this speed. Ignore any effects of air resistance. To use our speed and distance to find our time, we can use our usual velocity equation, solving this for time by swapping the v and t around. Putting in our numbers, where 1,000 kilometers is a million meters, gives me 55.56 or 56 seconds to two significant figures. Calculate the kinetic energy the asteroid would have at the moment of impact. Using our kinetic energy equation, knowing our mass and our velocity, gives us 4.374 times 10 to the 20, or 4.4 times 10 to the 20 joules to two significant figures. Discuss the energy transformations that would occur as the asteroid collides with Earth. The asteroid initially has kinetic energy. As it nears Earth, it would lose gravitational potential energy and gain more kinetic energy. As it strikes Earth, all its kinetic energy would convert into heat, sound, and the kinetic energy of ejected debris. Question 7. A bored physics teacher sits atop the 330 meter high sky tower, stacking 0.02 kilogram ballpoint pens. He accidentally drops one over the edge. If the pen reaches a terminal velocity of 15 meters per second, calculate its kinetic energy at this speed. Using our kinetic energy equation, putting in our mass and our velocity, gives me 2.25 or 2.3 joules to two significant figures. If we instead assume there is no air resistance, use kinematic equations to calculate the velocity of the pen just before it hits the ground. Because the pen is dropped, we know the initial velocity is 0, we know it accelerates due to gravity at negative 9.8 meters per second, it travels a distance of 330 meters downwards, and we're trying to find the final velocity. For this, we need to use a kinematic equation, where the thing we're not given and we don't care to find is our time, so we choose the one equation without it. Knowing that Vi is 0, this simplifies to Vf squared equals 2AD, square rooting both sides and putting our numbers in, gives me 80.42 or 80 meters per second to two significant figures. Using this velocity, calculate the kinetic energy of the pen just before it hits the ground. We have our kinetic energy, putting in our mass and our new velocity, gives us 64.67 or 65 joules to two significant figures. If the teacher instead drops a pen with twice the mass, discuss the effects this would have on the final velocity, ignoring air resistance. The gravitational acceleration of an object is not affected by its mass. Doubling the pen's mass will therefore not affect its acceleration, and will therefore not have an effect on the pen's final velocity. Gravitational potential energy. Question 1. Calculate the gravitational potential energy of the following. An 80 kilogram paraglider is hovering at a height of 200 meters above a valley. Using our gravitational potential energy equation and putting in our numbers, gives me 156,800 or 160,000 joules to two significant figures. A 12 kilogram satellite dish is mounted on a roof at a height of 15 meters. Once again using our gravitational potential energy equation, putting our numbers in, gives me 1764 or 1800 joules to two significant figures. Question 2. Determine the height of the following. A 0.7 kilogram keridu has 2.7 joules of gravitational potential energy when perched in a tree. Starting with our gravitational potential energy equation, solving this for height by dividing both sides by mg, putting our numbers in, gives me 0.4227 or 0.42 meters to two significant figures. A 5.2 kilogram toolbox has 60 joules of gravitational potential energy when lifted onto a bench. Once again, starting with our gravitational potential energy equation, solving for height by dividing both sides by mg, and putting our numbers in, gives me 1.177 or 1.2 meters to two significant figures. Question 3. Calculate the mass of the following. A scaffolding plank at a height of 4.6 meters has 190 joules of gravitational potential energy. Starting with our gravitational potential energy equation, solving this for mass by dividing both sides by gravity and the change in height, putting in our numbers, gives me 4.215 or 4.2 kilograms to two significant figures. Holly stands on a 50-meter dive platform with 19,000 joules of gravitational potential energy. Using our gravitational potential energy equation, once again solve for mass by dividing both sides by g delta h, putting in our numbers, gives me 38.78 or 39 kilograms to two significant figures. Question 4. During a flood response, a 20 kilogram sandbag is lifted 1.2 meters atop a barricade. Calculate the change in gravitational potential energy of the sandbag. Using our gravitational potential energy equation, putting in our mass, gravity, and the change in height, gives us 235.2 or 240 joules to two significant figures. How much energy would be gained if a 10 kilogram sandbag were raised to the same height? Because the mass and gravitational potential energy are proportional, halving the mass from 20 kilograms to 10 will also halve the gravitational potential energy from 240 to 120 joules. That is to say, if we have our potential energy equation, our height and our gravitational acceleration stay the same, such that if we halve our mass, we will also halve our gravitational potential energy. The floodwaters soon rise higher than expected, and the 20 kilogram sandbag needs to be moved to a new 1.8 meter high barrier. Calculate the increase in gravitational potential energy required. Our change in height is the difference between our two heights, which is 0.6 meters. Putting this into our gravitational potential energy equation, along with our mass and our gravitational acceleration, gives me 117.6 or 120 joules to two significant figures. Question 5. A 29 kilogram lawnmower is pushed up a slope to a height of 1.2 meters. Calculate the change in gravitational potential energy of the lawnmower. Using our gravitational potential energy equation, putting in our numbers, gives me 341.0 or 340 joules to two significant figures. How would the change in gravitational potential energy be different if a steeper slope was used to reach the same height? The change in height is the same, and a steeper slope would not change the mass or gravitational acceleration. Because our gravitational potential energy is mg times the change in height, the gravitational potential energy would not be different. That is to say that the mass is the same because we're using the same lawnmower, our gravitational acceleration stays the same, and we're moving the lawnmower to the same height, just taking a different path, which means that our gravitational potential energy must be the same. How would the change in gravitational potential energy be different if the lawnmower was pushed the same distance across flat ground? Pushing the lawnmower across flat ground would not affect its height. Since the change in height is therefore zero, and the gravitational potential energy is mg delta h, the gravitational potential energy of the lawnmower will not change. In other words, because delta h is zero, this whole side of the equation becomes zero, and we see that the change in gravitational potential energy is zero. Elastic potential energy. Question 1. Write an equation for K in terms of EP and X. Starting with our potential energy equation, we can solve this for K by doubling both sides and dividing by X squared. Question 2. Write an equation for X in terms of EP and K. Once again, starting with our potential energy equation, we can solve for X squared by doubling both sides and dividing by K, and finally by square rooting both sides. Question 3. Calculate the elastic potential energy stored in the following. A bungee cord with a spring constant of 100 newtons per meter stretches by 1.5 meters. Using our potential energy equation, we have our K and we have our X. Putting those numbers in gives me 112.5 or 110 joules to two significant figures. A garage door spring with a spring constant of 600 newtons per meter compresses by 0.1 meters. Starting again with our potential energy equation, we have both our K and our X values, which gives me 3 joules. Question 4. Calculate the displacement for the following. A catapult stores 150 joules of elastic potential energy with a spring constant of 120 newtons per meter. For this, we can use the equation that we found in question 2, put our numbers in, which gives me 1.581 or 1.6 meters to two significant figures. A pogo stick compresses, storing 90 joules of energy with a spring constant of 250 newtons per meter. Once again, starting with our solved X equation, we know both the EP and the K, which gives me 0.8485 or 0.85 meters to two significant figures. Question 5. Calculate the spring constant of the following. A trampoline stores 100 joules of energy when stretched by 0.5 meters. For this, we can use the equation that we found in question 1, where we have both our EP and our X, which gives me 800 newtons per meter. A bowstring stores 60 joules of energy when pulled back 0.3 meters. Once again, starting with our solved K equation, putting our numbers in gives me 1,333 or 1,300 newtons per meter to two significant figures. Question 6. A 10 kilogram baby is placed in a baby bouncer consisting of two identical springs. Each spring has a spring constant of 110 newtons per meter and stretches 40 centimeters. Calculate the force exerted by each spring. For this, we can use Hooke's law, where we have our spring constant, and although we have our extension, we need to convert this into 0.4 meters. Putting these numbers in gives me negative 44 newtons. Each spring makes an angle of 20 degrees to the vertical. Calculate the vertical force provided by each spring. We have our 44 Newton force at an angle of 20 degrees to the vertical, where our vertical component is what we're trying to find. Recognizing that 44 is our hypotenuse and the vertical component that we're trying to find is our adjacent, we can use the ka relationship in SOHCAHTOA, which is that cosine of the angle, is our adjacent, our force that we're trying to find, divided by our hypotenuse of 44. Rearranging this for our force by multiplying both sides by 44 gives me 41.35 or 41 newtons to two significant figures. Calculate the total support force on the baby from the floor. We know that our baby has a gravitational force, and part of that is going to be balanced by the forces from our two springs. But there's going to be some leftover component that's going to be balanced out by our support force. First of all, finding our gravitational force by taking the mass of the baby and multiplying that by gravity, putting our numbers in, gives me 98 newtons. And now recognizing that the up force must equal the down force, where our upwards forces are our support force that we're trying to find, plus the force from our springs, of which there are two. These must equal our down force, which is just our gravitational force. Solving this for our support force by subtracting 2F spring from both sides, putting our numbers in, gives me 15.3 or 15 newtons to two significant figures. Question 7. A footballer kicks a 0.45 kilogram ball into a goal. The ball strikes the net at 15 meters per second, causing the net to stretch by 0.25 meters. Calculate the kinetic energy of the ball as it strikes the net. We can start with our kinetic energy equation, where we know the mass and we know the velocity. That gives us 50.63 or 51 joules to two significant figures. Assuming all the ball's kinetic energy is converted into elastic potential energy, calculate the spring constant of the net. If all the kinetic energy is converted into elastic potential energy, then we know that these two equal, where we know that EP is half kx squared, and we can leave EK as EK because we found its value in the last question. Solving this for our spring constant, putting our numbers in, gives me 1620 or 1600 newtons per meter to two significant figures. Question 8. A 70 kilogram bungee jumper jumps off a bridge. The bungee cord has an unstretched length of 15 meters and a spring constant of 50 newtons per meter. Calculate the jumper's change in gravitational potential energy after they've fallen 15 meters. We can start with our gravitational potential energy equation, where we know all three of these numbers, which gives me 10,290 or 10,000 joules to two significant figures. Calculate the extension required for the force from the bungee cord to equal the gravitational force on the bungee jumper. First of all, we know gravitational force is mass times gravity. Putting in these numbers gives me 686 newtons. We can now use Hooke's law, where we know that the F must be the same as our gravitational force, and we know our spring constant, and we just want to solve for our X. We can do so by dividing both sides by K, putting our numbers in, gives me 13.72 or 14 meters to two significant figures. Describe the motion of the bungee jumper before, during, and after this moment. Before the force is balanced, the gravitational force is larger than the force from the bungee. The net force and acceleration are downwards, and therefore the bungee jumper's downwards velocity increases. And so we can imagine our bungee jumper. They will have a force of gravity, the size of which will not change, and there'll be a force from the bungee cord upwards, which will be opposing this force. Initially, as the bungee jumper falls, the size of the force from the bungee cord will be less than the gravitational force, and so the net force and acceleration would be downwards, causing them to accelerate and their velocity to increase. When the force is balanced, the net force is 0, and the bungee jumper briefly falls at a constant velocity. After the force is balanced, the force from the bungee grows larger than the gravitational force, such that the net force and acceleration are now upwards, and therefore the bungee jumper's downwards velocity decreases. And so we've reached a point where our bungee force is now greater than our gravitational, meaning that our net force and net acceleration are now upwards, in opposition to our downwards velocity, which will cause that downwards velocity to decrease. Calculate the elastic potential energy stored in the bungee cord after the bungee jumper has come to a rest. Using our elastic potential energy equation, where we know the spring constant, and we know that when the bungee jumper has come to a rest, the gravitational and bungee forces will balance. The extension at that point is what we found in part B. That gives us 4,706, or 4,700 joules to two significant figures. Conservation of energy. Question 1. Complete the energy flow diagrams below by filling in the missing energy values. Section A has a burning matchstick, where we have 1000 joules of chemical energy being converted into 150 joules of light energy and some amount of heat energy. This amount of energy is simply the energy left over from our 1000 after we've subtracted our 150 light energy, which is 850. Section B has a boiling kettle, which starts off with 150 kilojoules of electrical energy that is converted to 130 kilojoules of heat energy and some amount of sound energy. This amount is what's left over when you subtract 130 from our 150, which is 20 kilojoules. Section C has a bouncing basketball, where we start off with some amount of gravitational potential energy, and then as the ball falls, this is converted to 20 joules of kinetic energy. Because energy is conserved, that means our starting energy must have been 20 as well. As the ball bounces, we have 2 joules lost as heat energy, some amount lost as sound energy, and some amount lost as elastic potential energy. This unknown elastic potential energy is then converted into kinetic energy as the ball bounces upwards again, and because we know all of this energy must have come from here, these two must be equal, and so our elastic potential energy is 17. As our ball moves upwards, it comes to a stop, and all of its energy is now gravitational potential energy, and has been converted from our 17 joules of kinetic energy. Our final unknown is our amount of sound energy, which if we take our 20 joules, subtract 17 and subtract 2, we're left with 1 joule. Question 2. A 2.1 kilogram ball is dropped from a height of 10 meters. Calculate the kinetic energy of the ball just before it hits the ground, ignoring air resistance. We know that the kinetic energy our ball gains must equal the gravitational potential energy it lost. Gravitational potential energy is mgh, where we know all three, which gives us 205.8 or 210 joules to two significant figures. If the ball bounces to a height of 7 meters, calculate the energy lost. To find the energy after our bounce, knowing that it went to 7 meters, we can just find the corresponding gravitational potential energy. For this, we once again use E equals mgh, put in our numbers with our new height of 7 meters, which gives me 144.1 joules. And now to find the energy lost, we need to find the difference in the energy between the energy that it had at 10 meters and the energy that it ended up with at 7 meters. The difference between these two energies is 61.7 or 62 joules to two significant figures. Question 3. A football is kicked upwards at 25 meters per second. Calculate the height the ball will reach, ignoring air resistance. We know that our ball will have an initial kinetic energy, and that all of this energy is going to go into our gravitational potential energy. Knowing that kinetic energy is half mv squared and gravitational potential energy is mgh, we can divide both sides by our mass, which gets rid of it entirely, and now solve for our height by dividing both sides by g. Putting our numbers in gives me 31.89 or 32 meters to two significant figures. Calculate the velocity of the ball at half its maximum height. Half the height is just half of our height that we found in the last question, which is 15.95 meters. If we imagine the ball at its maximum height, if it fell a particular distance, our 15.95 meters, it's going to lose some amount of gravitational potential energy. This gravitational potential energy is going to be converted into our kinetic energy, which, using this equation, and once again substituting in the equations for each, we can divide out the mass and then solve for the velocity. To do so, we first double both sides and then square root both sides. Putting our numbers in gives me 17.68 or 18 meters per second to two significant figures. A 70 kilogram adrenaline junkie bungee jumps off Kawerau Bridge. The bungee cord has a spring constant of 150 newtons per meter, and its length increases by 30 meters as it stretches. Calculate the maximum elastic potential energy stored in the cord. The equation for our elastic potential energy is this one here. Knowing our spring constant and knowing our extension, that gives us 67,500 or 68,000 joules to two significant figures. Assuming energy is conserved during the jump, calculate the distance the bungee jumper fell. We know that our bungee jumper fell a certain height, and that at the top of this height they would have had some potential energy given by mgh. As they fell, this energy would be transferred into kinetic energy and then eventually end up as stored elastic potential energy in the bungee cord, which we found in the last question. And so we can solve this equation for h by dividing both sides by mg, putting our bungee energy in the equation, along with our mass and the acceleration due to gravity, gives us 98.40 or 98 meters to two significant figures. Question 5. A 9mm handgun fires bullets with a mass of 8.0 grams and a muzzle velocity of 370 meters per second. Calculate the kinetic energy of the bullet as it leaves the muzzle. We can first of all convert our 8 grams into kilograms by dividing 8 by 1000, and then knowing our kinetic energy equation and knowing both our mass and our velocity, we get 547.6 or 550 joules to two significant figures. Assuming no energy is lost to air resistance, calculate the height the bullet would need to be dropped to reach the same speed. And so, knowing this kinetic energy, we can use the gravitational potential energy equation and find the height associated with this energy. Solving for height by dividing both sides by mg, putting our numbers in, gives me 6,985 or 7,000 meters to two significant figures. Question 6. A 1,200 kilogram car stops at the highest point of the Auckland Harbour Bridge, 43 meters above sea level. The driver then puts the car into neutral and lets it roll without using the brakes. The car reaches the bottom and is now 15 meters above sea level. Calculate the change in gravitational potential energy experienced by the car. Our change in height is 43 minus 15, which is 28 meters. Using this to find our gravitational potential energy, putting our numbers in, gives me 329,300 or 330,000 joules to two significant figures. Assuming no energy losses, calculate the speed of the car at the bottom of the bridge. Knowing the change in gravitational potential energy, and knowing that this must have been converted into our kinetic energy, we can use our kinetic energy equation, solve it for our velocity by first doubling both sides, dividing both sides by the mass and square rooting. Putting our numbers in gives me 23.43 or 23 meters per second to two significant figures. Work. Question 1. Calculate the amount of work performed in the following. A gardener pushes a lawnmower with a force of 45 newtons across a lawn for 8 meters. Knowing that work is force times distance, and having both of these quantities, we get 360 joules. The spring in an air rifle is compressed by 0.12 meters with a force of 30 newtons. Once again, using that work is equal to force times distance, knowing both of these quantities, gives us 3.6 joules. A farmer drags a crate of apples 5.5 meters across a floor by exerting 40 newtons of force. Work is force times distance, our force is 40, our distance is 5.5, which gives me 220 joules. A rugby player pushes a tackling sled with a force of 120 newtons for 3.5 meters. Work is force times distance. Our rugby player applies a force of 120 over a distance of 3.5 meters, which gives me 420 joules. Question 2. A builder uses a pulley to lift a 40 kilogram bag of cement 7.2 meters upwards, while another builder carries an identical bag along an angled path to the same location. Calculate the work done against gravity by the builder using the pulley. Knowing that work is equal to force times distance, where the force that the builder is overcoming is the gravitational force from the bag, which we can find knowing that force is mass times gravity. Putting these numbers in gives us 392 newtons. Putting this into our work equation gives us 2,822 or 2,800 joules to two significant figures. Compare the work done against gravity by each builder. The mass of the bags is the same, so the gravitational force they are working against is the same. They both move the bags the same vertical distance, so the work they perform against gravity must be the same. Question 3. A helicopter lifts a bucket filled with water out of a lake to fight a fire. The bucket and water have a combined mass of 500 kilograms and are lifted to a height of 50 meters at a constant speed. What is the work done by the helicopter to lift the bucket of water to this height? To find our work, we can use force times distance, where the force is the gravitational force on our water bucket, which is mass times gravity. Putting in these numbers gives us 4,900 newtons. Putting that into our work equation gives us 245,000 joules or 250,000 joules to two significant figures. The helicopter later lifts a bucket with half the mass to the same height. How does the work done compare to the first lifted bucket? If the bucket has half the mass, it will experience half the gravitational force. Since work is equal to force times distance, and the height is the same, the amount of work required will be halved. In other words, since our gravitational acceleration is the same, if we were to halve the mass, we must halve the force, and if we lift it to the same height and we've halved the force, then we must halve the work. Question 4. Leo carries 20 kilogram bags of potting mix upstairs to his vegetable garden. Each bag moves a vertical distance of 3.6 meters. Calculate the gravitational potential energy gained by each bag. Gravitational potential energy is mgh. We know the mass, the acceleration due to gravity, and the height, which gives us 705.6 or 710 joules to two significant figures. Leo decides to try a longer 12-meter path up a gently sloping ramp. How does the gravitational potential energy gained by the bag compare to when Leo used the stairs? Although Leo takes the bag along a longer path, the distance moved against gravity is the same. Since E is equal to mgh and the mass of the bag does not change, the gravitational potential energy is the same. That is to say that if our mass is the same, and we know that our gravitational acceleration is constant, even though he's taken a longer path, our h here is purely the vertical distance, the distance moved against gravity. Because this is the same, that means that our gravitational potential energy must be the same. On his next trip, Leo drags the bag up the ramp instead of carrying it. He applies an additional steady force of 60 newtons to overcome friction. Calculate the total work done on the bag. We know our work done against gravity because we found it in part A. The work done against friction is going to be the force times distance, where the force is 60 newtons, and the distance over which it's applied is our 12-meter long ramp, which gives us 720. The total work done is just the sum of these two works, which is 1,426 or 1,400 joules to two significant figures. Power. Question 1. Calculate the power in the following situations. A wind turbine generates 24,000 joules of energy in 40 seconds. We know that power is work over time, we know the work, and we know the time, which gives us 600 watts. A drone lifts a 2.5 kilogram camera to a height of 12 meters in 8.5 seconds. Knowing that power is work over time, we have the time but we don't have the work. But we know that work is equal to force times distance, where we know our distance is 12 meters, and we know the force is gravitational, so it's equal to mass times gravity. Putting in these numbers gives me 294 joules. Putting that into our power equation gives me 34.59 or 35 watts to two significant figures. A ski lift races a 400 kilogram cable car 80 meters in 90 seconds. Once again, power is work over time. We know the time, but we need to find the work, which we can do again using work is equal to force times distance, knowing the distance, knowing the force is gravitational, so it's equal to mg, putting in these numbers, gives me 313,600 joules, putting that into our power equation, gives me 3,484, or 3,500 watts to two significant figures. Question 2. A 750 kilogram F1 car accelerates from rest at 15 meters per second. It travels 230 meters in 5.5 seconds. Calculate the force required to accelerate the car. We know that force is mass times acceleration. We know the mass and the acceleration, which gives us 11,250 or 11,000 newtons to two significant figures. Calculate the work done by the car to provide this acceleration. Work is force times distance. We just found the force and we were given the distance, which gives us 2.588 times 10 to the 6 or 2.6 times 10 to the 6 joules to two significant figures. Calculate the average power required to provide this acceleration. We know that power is work over time. We know the work, and we were given the time, which gives me 470,500 or 470,000 watts to two significant figures. Question 3. A solar panel is used to charge a smartphone. The smartphone's battery can store a maximum of 15,000 joules and is initially empty. The solar panel provides 5.8 watts of power. Calculate the time needed to charge the battery. Knowing that power is work over time, solving that for time by swapping our P and our T around, putting in our maximum energy and our power, gives me 2,586 or 2,600 seconds to two significant figures. Clouds reduce the solar panel's output to 3.1 watts. Calculate the additional time required to fully charge the battery from empty. Our new time can be found in the same way that we used in the last question, starting with our power equation, solving it for time, putting our numbers in with our new 3.1 watts, which gives me 4,839 seconds. And now to find the additional time, we need to find the difference between our new time and our last time. Putting those numbers in gives me 2,253 or 2,300 seconds to two significant figures. Question 4. A 600,000 kilogram Falcon 9 rocket and a 3,500 kilogram Sprint missile ascend at a constant speed to reach an altitude of 10,000 meters. The Falcon 9 takes 90 seconds and the missile takes 5 seconds. Calculate the gravitational potential energy the Falcon 9 rocket gains to reach this altitude. Gravitational potential energy is mgh. We know the mass, we know the acceleration due to gravity, and we know the height, which gives me 5.88 times 10 to the 10 or 5.9 times 10 to the 10 joules to two significant figures. Calculate the gravitational potential energy the Sprint missile gains to reach this altitude. Repeating the process, but with the mass of the Sprint missile, gives me 3.43 times 10 to the 8 or 3.4 times 10 to the 8 joules to two significant figures. Use calculations to determine which required the most power during its ascent. To find the Falcon 9 power, we recognize that the work is the gravitational potential energy that it gained, which it did in 90 seconds. Power is work over time. Putting these numbers in gives me 6.533 times 10 to the 8 or 6.5 times 10 to the 8 watts to two significant figures. Doing the same with our Sprint missile, we know our work and we know the time. Using our power equation, putting these numbers in, gives me 6.86 times 10 to the 7 or 6.9 times 10 to the 7 watts to two significant figures. And since we can see that this number is bigger than this number, the Falcon 9 rocket uses the most power. Momentum. Question 1. Calculate the momentum of the following objects. We have a volleyball with a mass of 0.27 kilograms, traveling at a velocity of 20 meters per second. Momentum is mass times velocity. Putting in both of these numbers gives me 5.4 kilogram meters per second. We have a train with a mass of 16,000 kilograms, traveling at a velocity of 3.1 meters per second. Momentum is mass times velocity. We know the mass and we know the velocity, which gives me 49,600 or 50,000 kilogram meters per second to two significant figures. We have a banana with a mass of 12 grams, traveling at 5.6 meters per second. Our mass of 12 grams can be converted into kilograms by dividing it by 1,000, which gives us 0.012 kilograms, which we can then use in our momentum equation, giving us 0.0672 or 0.067 kilogram meters per second to two significant figures. We have the moon with a mass of 7.3 times 10 to the 22 kilograms, traveling at a velocity of 1 kilometer per second. 1 kilometer per second is 1,000 meters per second. Since a kilometer is 1,000 meters, putting this into our momentum equation gives us 7.3 times 10 to the 25 kilogram meters per second. Question 2. A 7.2 kilogram bowling ball and a 56 gram tennis ball each move with a momentum of 110 kilogram meters per second. Calculate their velocities. In both cases, we can use our momentum equation, solving it for velocity by dividing both sides by our mass, substituting in our momentum and our individual masses, where 56 grams is 0.056 kilograms. That gives us 15.28 and 1,964, or 15 and 2,000 meters per second to two significant figures. Question 3. A 65 kilogram swimmer pushes off the wall of a swimming pool during a training session. Before contacting the wall, she glides at 1.8 meters per second. After the rebound, she moves away from the wall at 2.2 meters per second. Calculate the swimmer's momentum before she contacts the wall. Momentum is mass times velocity. We know the mass, we know the velocity, which gives us 117. Or 120 kilogram meters per second to two significant figures. Calculate the swimmer's momentum after she rebounds. Once again, using that momentum as mass times velocity, putting in our mass and putting in our velocity, gives us 143 or 140 kilogram meters per second to two significant figures. Calculate the change in momentum of the swimmer. We know our initial and our final momentums, however, because they're in the opposite direction, we need to make one of them negative. It doesn't matter which one, for reasons I'll explain at the end of the question. For this, I've chosen the final velocity. And now to find our change in momentum, that is final minus initial, putting in these numbers, gives me negative 260 kilogram meters per second. And now if I had instead made the final momentum positive and the initial momentum negative, we would have positive 143, and instead of negative 117, we would have positive 117. Our answer, instead of negative 260, would instead be positive 260. Both of these answers are perfectly correct. It just depends on which direction you've chosen to make positive. All this answer tells you is that our change in momentum is in the same direction as our final momentum. Question 4. The Japanese experimental spacecraft Icarus uses a solar sail to use the pressure of sunlight for propulsion in space. It has a mass of 315 kilograms. If the force on the solar sail is 0.0009 newtons, calculate the acceleration of the spacecraft. Knowing that force is equal to mass times acceleration, solving this for acceleration by dividing both sides by mass, putting in our force and our mass, gives me 2.857 times 10 to the minus 6, or 2.9 times 10 to the minus 6 meters per second to two significant figures. Calculate the change in velocity of the spacecraft after 24 hours. Knowing our acceleration, and knowing our time is 24 hours, which if we multiply that by 60 times 60, gives us 86,400 seconds. And now if we make our initial velocity 0, our final velocity is going to be our change in velocity. The one thing we don't have and we don't care to find is our distance, so we choose the one kinematic equation without it. Vi is 0, so this becomes AT. Putting in our numbers gives me 0.2468 or 0.25 meters per second to two significant figures. Calculate the change in momentum of the spacecraft after 24 hours. We know that momentum is mass times velocity. We know the mass and we know the change in velocity, which gives us 77.74 or 78 kilogram meters per second to two significant figures. Impulse. Question 1. Calculate the impulse experienced in the following situations, where by impulse we mean the quantity delta P. 15 newtons of force is used to stop a shopping trolley in 4.3 seconds. knowing our impulse equation, knowing our force and our duration, gives us 64.5 or 65 kilogram meters per second to two significant figures. An eel swims into a net and comes to a rest in 2.4 seconds with a force of 13 newtons. Once again, using our impulse equation, our force is 13, our time is 2.4, giving me 31.2 or 31 kilogram meters per second to two significant figures. Question 2. Calculate the average force experienced in the following situations. A skateboarder increases their momentum by 210 kilogram meters per second in 0.40 seconds. To find our average force, we can start with our impulse equation, solve it for force by dividing both sides by our time, putting in our momentum and our time, gives me 525 or 530 newtons to two significant figures. A 1.5 kilogram possum falls from a tree and lands in tall grass at 15 meters per second, stopping in 0.60 seconds. To find the change in momentum, this is the mass of the possum multiplied by the velocity it had when it hit the grass. Putting in these numbers gives me 22.5 kilogram meters per second. And now we can use our impulse equation, solve for force by dividing both sides by time, putting in our change in momentum and our time, gives me 37.5 or 38 newtons to two significant figures. Question 3. Calculate the duration of the following collisions. A 140 gram baseball, hit with 320 newtons of force, changes velocity from 20 meters per second to negative 30 meters per second. We know that our mass of 140 grams, if we divide it by 1,000, gives us 0.14 kilograms. We can find our initial and final momentums, knowing that momentum is mass times velocity, knowing the mass, and knowing our initial and final velocities, gives us 2.8 and negative 4.2 kilogram meters per second. And now to find our change in momentum, that is final minus initial, putting in these numbers, gives us negative 7.0 kilogram meters per second. Finally, we can use our impulse equation, solving it for time by dividing both sides by force, putting in our change in momentum and our force, and note that I've made our force negative 320 because we know that the force is in the direction of the final velocity, and our final velocity is also negative. That gives me 0.02188 or 0.022 seconds to two significant figures. A 10 kilogram robot vacuum, moving at 0.15 meters per second, hits a wall and stops with a force of 6.8 newtons. We can find the change in momentum, knowing the mass and knowing the change in velocity, which, because it starts with this velocity and then comes to a stop, is just going to be this velocity, giving me 1.5 kilogram meters per second, which we can use in our impulse equation, solve for time by dividing both sides by force, putting our numbers in, gives me 0.2206 or 0.22 seconds to two significant figures. Question 4. In 1972, a Serbian flight attendant survived an 11,000 meter fall after her plane exploded. The snow helped cushion her landing, allowing her to survive the impact. The terminal velocity of a falling person is approximately 55 meters per second. Assuming her mass to be 60 kilograms, calculate her momentum just before she landed. Momentum is mass times velocity. We know her mass, and we know the terminal velocity of a falling person, which gives us 3,300 kilogram meters per second. If the snow slowed her to a stop over 1.5 seconds, calculate the average force she would have experienced. Using our impulse equation, solving this for force by dividing both sides by delta t, putting in our numbers, gives me 2,200 newtons. Had she landed on solid ground, stopping in 0.1 seconds, calculate the average force she would have experienced. Once again, using our impulse equation, solve for force, using our same change in momentum, but this time our time of 0.1 seconds, gives me 33,000 newtons. Question 5. A group of thieves ram raid a local dairy. The 1,200 kilogram car hits the dairy at a speed of 8.1 meters per second and comes to a stop in 0.15 seconds. Calculate the impulse exerted on the car during the collision. Knowing that the change in momentum is mass times velocity, we know the mass and we know the change in velocity, which gives us 9,720 or 9,700 kilogram meters per second to two significant figures. Calculate the average force experienced by the car during the collision. Knowing our impulse equation, we can solve this for force by dividing both sides by delta t. Putting in our change in momentum and our time gives me 64,800 or 65,000 newtons to two significant figures. One of the thieves accidentally left his 2.3 kilogram physics textbook on the car's roof. Assuming there is negligible friction between the textbook and the roof as the car comes to a stop, describe how the collision affects the motion of the textbook. If there is negligible friction between the textbook and the roof as the car comes to a stop, the forces on the textbook will remain balanced and its motion will not change. Which is to say that if we have our textbook, we're going to have a gravitational force, which is going to be balanced by a support force, and as the car comes to a stop, because there's negligible friction between the textbook and the roof, it won't experience a force, and we know that we need a force in order for something to change its motion. The textbook initially moves with the car. When the car stops, the textbook will continue moving forward at a constant velocity. Question 6. During a severe hailstorm that struck Timaru in 2019, hailstones with a mass of 0.10 kilograms fell at a speed of 20 meters per second. Calculate the momentum of a single hailstone. Momentum is mass times velocity. Putting in our mass and our velocity gives us 0.20 kilogram meters per second. If 120 hailstones hit a parked car's roof in 1 second and come to a stop, calculate the impulse experienced by the car's roof. To find our impulse, we just need to take the impulse from one hailstone and multiply that by the 120 that we have in our 1 second, which gives me 24 kilogram meters per second. Calculate the average force exerted on the car's roof. We know our impulse equation, solving that for force by dividing both sides by delta t. Putting in our impulse and our 1 second gives us 24 newtons. Question 7. The Bloodhound LSR rocket car generates thrust by expelling 2.4 kilograms of exhaust gases behind it every second. The gases exit at a speed of 430 meters per second. Calculate the thrust force on the car due to the ejected gases. To do so, we can use our impulse equation, rearranged for force, where we know the time is 1 second, but we don't know the change in momentum every second. We can find this by knowing that momentum is mass times velocity, we know the velocity that the gases exit with, and we know the mass of the gases expelled every second, which gives us 1032 kilogram meters per second. Putting that into our force equation gives us 1032 or 1000 newtons to two significant figures. The initial mass of the car is 800 kilograms. Calculate the remaining mass after 30 seconds. To find the mass lost, we can take our mass lost every second of 2.4 kilograms and multiply that by 30 seconds, which gives us 72 kilograms. And now to find the remaining mass, we take the initial mass of our car, subtract our 72, to get 728 or 730 kilograms to two significant figures. Calculate the acceleration of the car after 30 seconds. We know the thrust force that the car generates, and we know the mass of the car after 30 seconds. To relate these to our acceleration, we can use F equals ma, dividing both sides by m to solve for our a. Putting our numbers in gives me 1.414 or 1.4 meters per second to two significant figures. The car runs out of fuel after 60 seconds. It applies brakes with a constant force of 1800 newtons and comes to a stop after 130 seconds. Calculate the maximum velocity of the car. To find the velocity of the car, we can use our equation for momentum, where momentum is mass times velocity, and using our impulse equation, it's also force times the change in time. Dividing both sides by mass gives us our solved equation, where we know the constant force. We know it comes to a stop after 130 seconds, so that's our delta t, but we don't know the mass of the car. To find the mass of the car after 60 seconds, we can take our initial mass of 800, and knowing that 2.4 kilograms of gas is lost every second, we can just multiply that by our 60 seconds that it took for the car to run out of fuel, which gives us 656 kilograms. Putting all these numbers in gives me 356.7 or 360 meters per second to two significant figures. Conservation of momentum. Question 1. Calculate the unknown velocities in the diagrams below. We have a situation before with a 0.5 kilogram cart traveling at 1.2 meters per second and a stationary purple cart of mass 0.7 kilograms. Afterwards, our carts stick together and they have an unknown velocity, which we're trying to find. To do so, we can recognize that momentum is conserved, so that the initial momentum must equal the final momentum. We can find our initial momentum because this is just the momentum of our pink cart, so we just need to take its mass times its velocity, both of which we have, which gives us 0.6 kilogram meters per second. And now we know our final momentum can be replaced with mass times velocity, where the velocity is what we're trying to find, and the mass is the combined masses of the trolleys. Solving this for our velocity by dividing both sides by m1 plus m2, putting our numbers in, gives us 0.5 meters per second. For section B, we have our 0.5 and 0.7 kilogram carts again, but this time our pink cart is traveling at 1 meters per second, and afterwards, instead of sticking together, the carts move in opposite directions. The pink cart moving at 0.4 meters per second, and the purple cart moving at a velocity that we need to find. Once again, we can calculate our initial momentum as just the mass of our pink cart times its velocity, which gives me 0.5 kilogram meters per second. And now to relate this to our momentums afterwards, we know because of conservation of momentum that the initial momentum must equal the final momentum, where the final momentum is the mass times velocity of each cart added together, where in this case v2 is what we're trying to find. Solving for v2 by first subtracting m1 v1 from both sides and then dividing both sides by m2. Putting our numbers in, we've decided to make this direction positive, which means that this direction is negative, and it means that this velocity is positive, and this velocity is negative. So we substitute in negative 0.4, which gives me 0.5 meters per second, and because it's positive, we know that it must be traveling in this direction, as we would expect. For section C, our two carts are joined with a spring, and because they're initially stationary, our initial momentum is 0. Afterwards, the carts spring apart, the pink cart with a velocity of 2 meters per second towards the left, and the purple cart with an unknown velocity towards the right, which we're trying to find. Assuming conservation of momentum, our initial momentum must equal our final, where our final momentum is just the sum of the mass times velocities of our carts. v2 is what we're trying to find, so we can solve that by first subtracting m1 v1 from both sides, and then dividing by m2. Once again, we decide that this direction is positive and this direction is negative, which means our 2 meters per second is negative. Putting those numbers in gives me 1.429 or 1.4 meters per second to two significant figures. Question 2. 66 million years ago, an asteroid struck Earth, leading to the extinction of the dinosaurs. The asteroid had an estimated mass of 1.0 times 10 to the 15 kilograms and struck Earth with a speed of 20 kilometers per second. The mass of the Earth is approximately 6.0 times 10 to the 24 kilograms. Calculate the momentum of the asteroid just before it struck Earth. Our velocity of 20 kilometers per second, multiplying that by 1,000, gives us 20,000 meters per second. And now to find the momentum, we can just use mass times velocity. Putting in these numbers gives me 2.0 times 10 to the 19 kilogram meters per second. Assuming the asteroid and Earth combined into a single object after the impact, calculate the change in Earth's velocity. Assuming conservation of momentum, our initial momentum must equal our final, since the asteroid and the Earth combine into a single object, is going to be their combined masses multiplied by their combined velocity. Solving this for our combined velocity by dividing both sides by ma plus me, putting our numbers in, gives me 3.333 times 10 to the minus 6, or 3.3 times 10 to the minus 6 meters per second to two significant figures. Question 3. A 90 kilogram man and a 40 kilogram boy collide head-on in 300 kilogram bumper cars and come to a stop. What physical quantity is conserved during the collision? This is momentum. State the total momentum after the collision. Because they come to a stop, their momentum must be 0. State the total momentum before the collision. Because we know that momentum is conserved, that means that the momentum after the collision must equal the momentum before the collision, and so our momentum must also be 0. If the man's car was traveling at 0.51 meters per second, calculate the initial speed of the boy's car. We can first of all find our combined masses of our man and our boy by taking their masses and adding on the mass of the bumper car, which gives us 390 and 340 kilograms. And now, assuming that momentum is conserved, we know the initial and final momentums must equal. Knowing that our final momentum is 0, because they come to a stop, we can write our initial momentum as the mass times velocity of the man and the boy. Solving for the velocity of the boy by first subtracting vm from both sides and then dividing both sides by mb. Putting our numbers in gives me negative 0.585 or negative 0.59 meters per second to two significant figures. A 30 kilogram girl in another car collides and joins with them. They move together with a velocity of 0.44 meters per second. Calculate the speed of the girl before the collision. First of all, finding the mass of the girl and her bumper car by taking their masses and adding them together gives us 330 kilograms. And now assuming that momentum is conserved, because before the girl hit, the man and the boy are stationary, they won't have any momentum, and therefore the only initial momentum will be from the girl. After the collision, they move off as a combined object with a combined mass and a combined velocity. Solving this for Vg by dividing both sides by mg, putting our numbers in, gives me 1.413 or 1.4 meters per second to two significant figures. Question 4. NASA's DART probe was designed to crash into an asteroid to study how it might be deflected. The probe had a mass of 610 kilograms and impacted the 5.0 times 10 to the 9 kilogram asteroid Dimorphos at 6,600 meters per second. Calculate the momentum of the probe just before impact. Momentum is mass times velocity. We know the mass of the probe, and we know the velocity of the probe, which gives us 4.026 times 10 to the 6, or 4.0 times 10 to the 6 kilogram meters per second to two significant figures. Assuming the asteroid was initially stationary, state the combined momentum of the probe and asteroid immediately after the impact. If the asteroid was initially stationary, then the only thing moving was our probe. And so the total momentum initially is what we found in part A, and since we can assume that momentum is conserved, this must be the momentum after the impact. Calculate the velocity of the combined probe and asteroid after the impact. Knowing that our initial momentum was 4.026 times 10 to the 6 kilogram meters per second, and knowing that momentum is conserved, we can write our final combined momentum as the combined mass times their combined velocity. To find this combined velocity, we can divide both sides by mp plus ma, put in our numbers, which gives me 8.052 times 10 to the minus 4, or 8.1 times 10 to the minus 4 meters per second to two significant figures. Question 5. A bulletproof superhero is standing still while being hit by 50 bullets every second. Each bullet has a mass of 10 grams and is moving at 300 meters per second before it hits the superhero. Calculate the momentum of each bullet before it hits the superhero. Our mass of 10 grams can be divided by 1,000 to find 0.01 kilograms. Momentum is mass times velocity. Putting in our mass and our velocity gives us 3.0 kilogram meters per second. Assuming the bullets fall to the ground after impact, Calculate the change in momentum the superhero experiences every second. Knowing the momentum from each bullet, we can find our change in momentum by multiplying this by the amount of bullets every second, which as stated up here is 50. That gives us 150 kilogram meters per second. Calculate the friction force the superhero needs with the ground in order to remain stationary. Using our impulse equation, we can relate our force with a change in momentum over a particular duration, where we know that our momentum changes by 150 every second. And so rearranging this equation for force by dividing both sides by delta t, putting in our 150 and 1 second, gives us 150 newtons. Calculate how this force would need to change if instead of stopping, the bullets bounce off the superhero in the opposite direction with the same speed. If the bullets bounce off with the same speed, that means they bounce off with the same momentum. And so as the bullets come in, they have a particular momentum. We therefore need to change the momentum in the opposite direction to cancel this out. And then to get the bullet moving at the same speed, we need to once again add the same amount of momentum. And so as we can see, the momentum change doubles. So we can take our 150 and multiply it by 2, which gives us 300 kilogram meters per second. And now redoing our force equation that we used over here, this time with 300 instead of 150, gives us 300 newtons, and so the force is doubled. Question 6. Famed space pirate Captain Blondebeard punctures a hole in his suit to propel himself from rest towards his rescue ship. He ejects 500 grams of air behind him at a velocity of 380 meters per second. Captain Blondebeard and his suit have a combined mass of 120 kilograms. Calculate the change in velocity of Captain Blondebeard. We know the mass of our air is 500 grams, which dividing this by 1000 gives us 0.5 kilograms. And now knowing that the momentum of the air expelled must equal the momentum gained by Captain Blondebeard, we can replace these with their masses times their velocities, where the velocity of Captain Blondebeard is what we're trying to find. So we can divide both sides by mb, put in our numbers, which gives me 1.583, or 1.6 meters per second to two significant figures. Captain Blondebeard collides and holds onto his waiting 97 kilogram crewmate, causing them to move together with a velocity of 0.7 meters per second. Calculate the initial velocity of the crewmate. Assuming conservation of momentum, we know that the momentum of Captain Blondebeard plus the momentum of the crewmate must equal their final combined momentum. Substituting in our masses times our velocities, where our final mass is the combined mass. And now solving this for VC, which is what we're trying to find, by first subtracting MBVB from both sides, and then dividing both sides by MC, putting our numbers in, gives me negative 0.3924, or negative 0.39 meters per second to two significant figures. The negative tells us the direction that the crewmate was traveling in. And so initially we have our Blondebeard moving with a momentum that we decided to make positive. We decided this when we wrote his velocity as positive. Because our crewmate's velocity is negative, that means the crewmate must have been moving in the opposite direction. Question 7. A boat cleaner water blasts the side of a boat while standing on a floating raft. The water hits the boat at a right angle with a velocity of 40 meters per second and a rate of 0.7 kilograms per second. The water blaster is operated for 5 seconds, assuming the water stops as it strikes the boat. Calculate the total impulse exerted on the boat during this time. We know that we have a mass of 0.7 per second, and if we have 5 seconds, we just multiply this by 5 to find a total mass of 3.5 kilograms. And now to find our impulse, we can use that equals mass times velocity, where we know the mass, and we know the water's velocity, which gives us 140 kilogram meters per second. State the change in momentum experienced by the cleaner and raft system. Because of conservation of momentum, the momentum gained by the water and later imparted onto the boat must be equal to the momentum gained by the cleaner and raft system, but in the opposite direction. So if we were to have our boat and our cleaner on the raft with their water blaster, the water is given a momentum of 140 in this direction, which means that the cleaner and the raft must be given the same momentum in the opposite direction, which is 140. The cleaner and raft have a combined mass of 90 kilograms. Calculate their change in velocity over 5 seconds. We can use our momentum equation, solving that for our velocity by dividing both sides by the mass, putting in the change in momentum, and the mass that we were just given gives us 1.555 or 1.6 kilogram meters per second to two significant figures. If the water instead bounces off as it strikes the boat, explain how this would affect the momentum of the boat. If the water bounces off the boat, it will experience a greater change in velocity, since not only would the water go from moving to not, requiring a change equal and opposite to the water's velocity, because it's now bouncing off with some velocity, its change in velocity will be increased. And since momentum is mass times velocity, this will result in a greater change in momentum. As momentum is conserved, the increased change in momentum of the water will result in an equal and opposite increased change in momentum of the boat.